Hi, everyone. So this session is entitled Types and Monads, which is probably the two biggest themes in Haskell development since its inception. Many of us have heard of free monads and freer monads, but of course monads are not so amenable to static analysis. So here we have Grant van Dommelen, who will talk to us about freer arrows and why we need them. Oh, you don't need that, you can use that.
All right. Hello everyone. My name's Grant van Dommelen. I'm a PhD student at Portland State University, and I'm going to be talking to you about freer arrows. So, for a little bit of context, let's say that I am in a situation where I want to write a program with effects, and I decide I want to create an embedded domain-specific language, and I know the kinds of effects that I want to include. I can encode my effect something like this, where I have two different events, one for reading an integer from somewhere, and one for taking an integer and writing it. I'm going to be calling the data structures like read-write effects, and these two constructors, read and write, are the events in the effect. This is the format that you would use if you wanted to put an effect in a freer monad, which is defined like this, or this is one of the implementations of freer monads. We have two constructors that roughly correspond to the return and bind operations from the monad type class. One thing to note, though, is that in bind, we always start with an effect. It's e of x. Do I have all these? Yeah, e of x. And we continue with this function that takes in an x as an input. So if I wanted to write a program using this read-write effect, I could use the bind constructor, bind the output of reading an integer to a variable x, and then write using that same x, and then return, say, unit. I could also write in do notation, which is probably the more common way to write that, but we need something to embed the effect into the freer monad. So embed is a nice way to do that. We have some advantages in writing our code this way. It's simple to set up. We just need to define the effect, and we can plug it into the freer monad. We get a sequence of events represented syntactically with the constructors for bind and return. And we can run this in another monad by interpreting our effect into that other monad. We could even give multiple interpretations into different monads or into the same monad, very flexible. So what's missing? We have a challenge with static analysis. If we look again at this bind constructor, the continuation takes in the type of the output of the effect. So we need to have a value of that type to be able to know what event's going to come next. So we can't inspect inside the continuation without running that function, without having an object of that type. So if we wanted to do static analysis on this, we either have to run the whole computation, or our static analyzer can't be a Haskell function. So our solution that we propose is freer arrows. I just gave you a little bit of background on freer monads. I'm going to continue with a brief introduction to freer arrows, and a little bit of explanation on why we think that freer arrows can be useful. So, starting with an introduction, we make some contributions in our paper. We propose the freer arrows data structure for writing embedded domain-specific languages in Haskell, and we study how they can be used and explore different implementations and interfaces that you can use to interact with them. So, let's take a look at another version of this read-write effect. This time, there are two type parameters, one representing the input type and the output type. And our read event now takes in a unit and outputs an int, and our write takes in int and outputs a unit. We can use it in our freer arrow data structure, whose implementation I have here. And you don't need to understand this all at once. I'm going to explain the parts that are relevant. So just like freer monads give you a monad instance for free with your effect data type, the freer arrow is going to give you an arrow instance for free. If you're not familiar with arrows, the simplest example of an arrow is the function arrow. And the constructors of freer arrow resemble some of the arrow type class functions. In particular, ARR lifts a pure function into the arrow, and we have composition from the category type class. These are represented by these constructors. Hom, we lift a pure function into the arrow, and composition, we take a pure function, and I'll explain why this looks this way in a little bit, and an effect that goes from A to B. And this third argument acts as a continuation for how to continue on with the computation. And we package it all up into a freer arrow from some type X to some type Y. So looking at this composition constructor, our first argument is a pure computation which returns a pair. So it's kind of doing two things. We can do whatever we want to the input as long as at the end we package it up into a pair. And the reason we do this is that the effect takes in an A as an input, and sometimes we want to have a part of the input that doesn't run through the effect. So we separate it into a part A, which runs through the effect, and a part C, which kind of passes it by. Then, for our third argument, it's like a continuation, but it's another object of the type freer arrow. So we'll see another constructor that we can potentially match on. The input to the continuation is both a pair B, which got transformed from the A, and a C, which was left untouched. Yeah, so freer arrows, like freer monads, can be run by interpretation, but we interpret it into another arrow instead of a monad. This ends up being really easy because any monad has a trivial arrow that we can derive from it, the Kleisli arrow. And so we can still interpret it into a monad like IO, which we'll need to do if we want to have the ability to use the IO monad. Then we can write some functions in a similar way as before. Here I'm writing it out with constructors again. One of the caveats is that we do need to still take our input and turn it into a pair. So this is going to look really messy at first. So we'll compose the read event into the write event. We don't need to do anything with the input going to the write event because we already got the input on the left side of the pair from read. And then at the end, if we want to return unit, we can use the hom constructor to finish with a pure computation. Yeah. This ends up being like a list of events, which will run in order, ending with a pure computation. The pure computations happen before every effect, so we kind of get an alternation between the pure and impure computations. And there are a couple different ways to write this because this is really messy. We can use the category notation with the forward composition operator. You could also use the regular composition operator if you're more comfortable. And we have another version of this embed function, but for arrows. You could also write it with the arrow do notation, which is a little bit more explicit about where the data flows in the notations. We have to explicitly say which things in the environment pass into each event. So it looks a little noisier than the monad version, but it's doing roughly the same thing. Okay, so now I'm going to talk about what freer arrows can be used for. And the first thing we're going to focus on is static analysis. So what kind of static analysis can we do? We can write simple recursive functions on the structure of the freer arrow. For example, if we wanted a function that could count the number of events, we could write that simply with a recursive function. We know that there are going to be no events in the pure part that ends in the hom constructor. And then each comp constructor represents one event. This is just representative of the kind of pure functions you can write. We're probably not usually going to want to be just counting events. We could also have functions that modify the computation. So we could have a function that takes a Fourier arrow as an input and outputs another Fourier arrow, maybe with some domain-specific optimizations. We'll talk about that a little bit more later. One thing that we were able to do, which was really fun, is summarize the events in a monoid. So if you have a function which can kind of take a event and for any input and output type, convert it into an object in a monoid, then we can collect all of the events into that monoid. So for example, you could collect them all into a list and get a list of all the events that will happen. But I have to comment on expressiveness. There is a cost to all of this. Fourier arrows trade off their expressiveness for static and analyzability. Because the more an abstraction does, the less we know about it. Fourier monads had the flexibility of that continuation where, based on the output of any event, we could decide later on what the next event or the next computation that will happen will be. The arrows are more expressive than implicative functors, but less than monads. And in particular, our Fourier arrow, like I said, it's like a list of events. And in the version I showed you, each of those events will happen, and they'll happen in order. We do construct two additional variants, one weaker, a Fourier pre-arrow, and one more powerful, a Fourier choice arrow. A Fourier choice arrow is one that I'll talk about later, and it gives us a little bit of ability to have more expressiveness. We can have events that might or might not run. But first, do we have any real examples using Fourier arrows? Of course. We did a case study in choreographic programming, and we used the library Haskell for choreographic programming in Haskell. I'll start with a little bit of a summary of Haskell so that we can understand kind of the language that we're talking about. In choreographic programming, we have a computation that's going to be running on multiple machines or multiple participants. I'm going to be calling them endpoints, as the library does. And they work together to compute something. So the great thing about choreographic programming is that the program is written once for all of the endpoints, and it's executed differently at each one. The original Haskell library is implemented using Fourier monads. In particular, we have the choreo monad and the network monad. The choreo monad, it's not super important what the events are. I'll list them here just to get an idea of them. You can do local computation on one endpoint. You can send data back and forth between endpoints. And there's a special event for synchronizing choices between the endpoints so that they're always in sync as we go through the computation. The network monad is the type of programs projected out. So whereas the choreo monad, all the events are from a global perspective, and the network monad, they're from the perspective of just one endpoint, the one that will be running. So similar to the ones in the choreo monad, run has a computation in the underlying monad M, kind of corresponds to local. Send and receive are the two kind of parts of sending data from one endpoint to another. And broadcasting is the way that we implement synchronizing choice. Here's an example choreography, just so you can look at one for a little bit. You don't really have to understand this, but you can see there's Alice and Bob get talked about, and this is a sort of version of the echo example I have earlier, but in this case, Alice is the one to read an input, which gets sent to Bob, and Bob's the one that writes it. In Haskell, the thing that is used to send the computation to each of the endpoints is called endpoint projection. We take an instance of the choreo monad and the location we want to project it to, and then we get the instance of the network monad. Endpoint projection specializes the choreography to one endpoint. And it kind of looks like this, although I'll show you later, this is a little bit of a lie. But if you were to write programs in the network monad representing the ones that get projected, you would have two different versions, like one for Alice and one for Bob, using the network events instead of the choreo events. There's one limitation to endpoint projection in the original Haskell library. The recursive call to endpoint projection is partially applied. So it's dynamic, and it waits for the output of each event to continue projecting the choreography to whichever endpoint is running it. Ideally, the endpoint projection would be static and be able to run fully before starting to run the computation. And separately, the choices must be broadcast to all endpoints, even if they don't need to know about them. Our solution to these problems is also freer arrows. We replace the freer monads with freer arrows in Haskell, and most of the interface remains largely the same. This was one of the big advantages. We ended up with two versions, one with choice and one without. It turns out that we could probably use the version with choice most of the time. Without choice, though, we don't want to be synchronizing branches because there are none, so we don't need the cond event or the broadcast event from choreo and network, respectively. So using freer arrows, that echo example we wrote earlier would be written like this. Here I've chosen to write it with the arrow type class notation instead of the arrow do notation, but that's not really important. You can use either one of them. And we get one benefit which is called selective broadcasting. So when we do have a program, this is one using the monadic version of Haskell. Sometimes we have branches, and the cond event here is what synchronizes the branches so that each endpoint can follow along with what to do next. In this example, we have a simple key value store, which has three participants: the client, which is going to be using the key value store, the primary endpoint, which is going to be handling, storing the data, and giving it back to the client, and then a backup to kind of mirror all of the data on the primary. One thing to notice is that this cond branch uses some data from the primary endpoint, but if you look inside the body, we only see the primary and the backup being referenced. There's no reference to client. Their behavior is exactly the same regardless of which of these branches runs, excuse me. But cond in the original Haskell library ends up broadcasting to client, even though they're not involved in that part of the choreography. With our arrow version, we can write functions like this participants function, which can actually inspect the body of a cond branch and see which endpoints are actually involved in that branch. Then during endpoint projection, we can use this function and have broadcasts that only broadcast to the parties that need to know about the branch. So in the key value store example, the client doesn't need to see what branch is taken. We can just broadcast that choice to the backup from the primary. It's a little cut off at the bottom. Yeah, so with Haskell using freer arrows, we get a few main benefits. One is that endpoint projection is static in the sense that it can run fully before we start running the program. Of course, everything I'm talking about here is technically still happening at runtime because we're not using any kind of staged programming or metaprogramming. But we don't have that effect where we're alternating projecting the choreography and running it on one of the endpoints. We could imagine two stages, even if they're both happening at runtime. We also get selective broadcasting, like I just talked about. The cond events can be translated during endpoint projection to only broadcast to the parties that need it. We could do static profiling if we wanted to. We can, without needing to run examples of the choreographies, we could construct them and then inspect them to see how many events are running if we project them to the endpoints, we can see how many sends and receives or local computations happen on each one without ever needing to like simulate it. And we could also do some kinds of optimizations. We experimented with one of them where we take two sends that happen between the same two locations, and we could combine them. So maybe in a setting where you wanted to reduce the number of times you communicate over the network, that would be potentially a useful optimization. Yeah, so in conclusion, freer arrows seem to be useful for writing embedded domain-specific languages for effective computations. They do trade off expressiveness for static analysis. You can do operations similar to what can be performed in an abstract syntax tree. One note on that is that it's not an abstract syntax tree. The version that we propose is normalizing, so the events are in kind of a list more than a tree. They have an interface similar to Fourier monads, and you can sometimes use them as a nearly drop-in replacement. And you can use Haskell functions for static analysis instead of needing any metaprogramming or GHC plugins or anything like that. So we have more in the paper. Feel free to scan the QR code, read our paper. There's some cool things in there, and if you look in the appendix is separate, but there's some cool things in there as well. We're working on some future work. We'd like to explore more variants of the Fourier arrows and see if we can get like a single version, but feel free to talk to me after the talk if you want to. Yeah, thank you.
Any questions?
So I have two questions. One is more concrete and one more open-ended. So the concrete one is, do you have any examples of Haskell programs that cannot be rewritten in the arrow style?
Well, I mean, out of the examples in the Haskell repository, I think we found that several of them couldn't, because a lot of them use recursion or iteration to do something, and that's not supported by the Fourier arrow data structure by itself. We do have a note in our paper that you can combine it with another data structure, for example, for iteration. We were able to come back from that, but we don't have any, like we didn't call out any specific examples of programs we can't write.
Right. Well, I meant more like more really where it can't possibly be made to. Yeah. Okay. So my other question was, oh shit, what was my other question? Maybe. Oh yes. So in the arrow type class, there are situations where it's not good that the R method is in the arrow type class because it means that you can't interpret, like you can't use arrows to write things that you want to interpret as something other than a Haskell function. And it seems that this freer monad construction bakes in more pure functions everywhere, mainly to do the first, second thing, right?
Yes.
So okay, so do you have any, like, does this approach give you any road towards if there was an arrow type class that didn't have R as a method, could this be still applied, or would you still end up with these pure functions just to do the packing?
Yeah, this is something that we were exploring as ways to mitigate what you were talking about. It didn't end up making it into the paper, but we were looking at ways to maybe do some defunctionalization to get a little bit of better ability to like analyze those pure functions as well. I'd be happy to talk about that offline if you'd like, but yeah, we have some future work that we're looking at that.
Thanks.
Yeah.
Nice talk. I really like Haskell as a way, people implement various choreographic languages, and they're not widely used. You should implement your own language. So doing it as a library, I think, is a fantastic idea. One comment and one question. So the comment is just, well, John Hughes originally invented arrows in order to do some static analysis of parsing. So this is right in line with the original reason for arrows. So the reason here for using an arrow is not to be able to, you said, I want to do static analysis, but presumably the reason for doing static analysis is it makes things run faster?
I'm not very familiar with benchmarking Haskell. We did try to do a little bit of that. We think that it would make things run faster because we're, expecting that certain static parts get, evaluated once instead of multiple times. We had some benchmarks that maybe showed that, but compared to monads, we weren't really sure. It seemed like monads were winning out in kind of mysterious ways.
Is there any other reason for doing static analysis rather than to make things run faster?
Well, I mean, we're hoping that there's some applications in like program verification as well. That's the kind of topic that I'm most interested in. We haven't looked very much into that, but yeah, we're hoping that we can do stuff in that kind of realm.
Don't you need the static analysis to do the projection part? That's fundamental. You do.
Or,
That's a better answer to Bill's question.
sorry, can you repeat that? Sorry.
Don't you need to do a static analysis to do the projection part?
No, they don't.
Yeah, the original Haskell library does endpoint projection without doing the static analysis. But it does it, like I said, alternating at runtime with the running the projected program.
So there really should be some graphs in this paper to show it goes faster. And if they're not, then your conclusion is, here, we thought we had arrows, we thought they'd make things better, but of course they're less expressive than monads. Turns out monads run just as fast, so don't bother with arrows. That's a perfectly reasonable conclusion, if it's true. I don't know.
Yeah, we'll have to look into that.
If there's, oh, go ahead. Okay, so no, there are not any graphs in this paper. We had a different paper at PLDI earlier this year that had another mechanism for making Haskell's broadcast more efficient, but not like this. Instead, it required programmer-added annotations to say who was participating in a conditional. And we do have some empirical results that said that that made things faster because there was less message traffic. So in principle, we should get good results like that from this too, but I don't actually have that data.
Have you, is this on?
Yeah.
Yep. Have you considered freer applicatives rather than freer arrows?
Yes, we have. And actually, that's one of the reasons that we use this echo example is this is one that we cannot write using applicatives or freer applicatives. I think I made a note here somewhere that arrows sit between monads and applicatives in expressiveness.
He wrote that paper.
Oh, yes. Oh, yeah, hello. But yeah, but we did start, that was where we started, is we were exploring applicatives, found out that we couldn't do what we wanted to, and then discovered arrows as an alternative.
Is there, is there anything useful to be done with applicatives, or is it just too impoverished?
I mean, I think there were definitely good results with applicatives. I mean, I think, yeah. What was that? The echo example, yeah. Let's see if I can find. I'll show this version. I know there have been good applications in parsing.
No, I mean in your application area.
Yeah, I'm not really sure. Like I said,
Okay.
we made an attempt and it didn't work out, and that's where we discovered arrows. Yeah.
Fair enough.
Thank you.
So I wonder how this approach compared to tracking the effects in the types. Like you can, for example, you can track how many echoes you have sent using typelets, right? So that allows you to do static analysis, and also I think that gives you more control. Like you can more precisely specify what you can do and what you cannot do, right? You can say to transition from this type, like from this state to that state, you have to perform that particular effect. So I wonder, like, curious what you think about that.
Yeah, I think that's an interesting approach as well. It kind of looks like staged programming in a sense because the types are resolved at compile time instead of at runtime. But yeah, I think that's another approach that would also work. Yeah.
Okay, sorry, one more question. So you have this harm constructor where you can lift any Haskell function into your Fourier arrow. Do you find that to compromise your ability to perform static analysis, or is that not something?
Yes, it definitely does. I think these pure functions act as a kind of barrier to that static analysis, especially because a lot of the time it seems like what you want to do with that ARA constructor is kind of routing for the data. That's why we were looking into some defunctionalization techniques or something like that. But as long as you're using that R function, there's not really much you can do to defunctionalize it without using something else in GHC. Yeah.
Last one. Since you have this slide up,
Yes.
can you just comment a bit on the arrow tax, which is that if you write programs using arrows, you often find that the meaningful part of the program gets submerged in a sea of encrustations of firsts and seconds and plumbing, and the arrow notation in your bottom thing was meant to address that. But I don't feel as if I've got any practical experience about how much of a problem it is and how effectively the proc notation deals with it. I'd just be interested in your practical experience, programming at scale with arrows.
Yeah, we were very hopeful with the proc notation in that it did simplify that kind of tracking the dependencies of the data flowing through the computation. But what we found was that there were some challenges, especially in that it produced code that was kind of unexpected in certain ways. And this kind of really came out when we were trying to do some of those domain-specific optimizations, because we would expect two events to be next to each other when they really weren't, because
What was it? It desugared into a mass of firsts and seconds, yes.
And one of the big things about that is that it did use that ARR constructor, or not constructor, type class function, and especially in our future work, we were looking at defunctionalization. It basically didn't work at all. We lost all of the benefits of defunctionalization.
So how can we fix this problem that you've discovered?
Yeah, I'm not sure. I'm not very familiar with GHC internals, but we were thinking about looking at specializing the proc do notation so that maybe we could replace that instances of the ARR function calls. It would be really nice if it used first and second whenever possible, because we can at least override what those generate. But like I said, I'm not very familiar with GHC plugins or GHC internals.
That's all we have time for questions, but let's thank Grant once again. Okay, Anton, are you here? There you are. Okay. Okay, so our next speaker, come on. All right, great. Our next speaker is Anton Lorentzen from the University of Edinburgh, and he'll be talking about property-based testing, but not as we might be familiar with it. Instead, it's about amortized time complexity. So take it away, Anton.
Yeah, thank you, Liam. I have probably one of the longest paper titles at this conference. And it basically chains together a bunch of concepts. So lightweight testing, you can already see, I'll use quick check later in my talk. Amortized time complexity, in particular the persistent one that Okazaki studied. And then I'll present something new, which I call the credit monad. But to start with, I want to start with the amortized time complexity, and I want to explain why that's a concept that matters. So let's look at probably the simplest queue you can imagine in Haskell, and you've probably written a program like this. So if you want to have a queue in Haskell, you take two lists, a front list and a back list. You push by putting something onto the back list, and you pop from the queue by taking something from the front. And you can already see that that probably doesn't work very long, because if you only push to the back and you only take from the front, at some point the front will be empty. And so you'll add this extra function called queue that checks that whenever your front list is empty, you'll reverse the back list and install that as the new front list. And so that is a very simple and functional implementation of having a queue. But it does have a bit of a problem, namely that the worst case runtime of this is not so good. So of course pushing is very quick, you just add a constructor there, but then popping can be quite expensive because you might have to reverse the entire back list. And so the question is this actually a good queue implementation after all? And so if we think about this worst case, we might think actually not, right? Any individual pop operation might take a long time. And now we might worry, you know, what if we do a bunch of like n push operations and m pop operations? What is the runtime of all of this? And you might worry that it's n times m, which would of course be very bad. But you can kind of convince yourself that it's actually not so bad, because every element is put onto the real list and will be reversed at some point onto the front, and that can only happen once. So if you kind of look at this in a combined manner, like n push and n pop operations, well, you have to pay for n push operations, and you have to pay for n reversals, potentially, and then for m pops, which is, of course, a much better runtime than the n times m you might have imagined naively, right? And so in an amortized sense, we might say pop takes O of one time. And so the way you can make this argument precise is by reasoning about credits. So let's say we look at this example. So we have a queue, so we push 1, 2, 3, 4 into the empty queue, and then we take one element out. So we start with the empty queue, and we push one element in, and we immediately have to reverse it onto the front. And then we push one element into the backlist. And so here we have to do no work for the reversal, but I'll kind of pretend that we do, and I'll accumulate this credit, which I've marked by this coin there. And so I keep pushing until I have 3 elements in the real list, and then I have 3 credits accumulated. And now, once I actually do the pop, well, I can kind of say that the pop is free, because of course I have to do this big reversal, but instead of kind of paying for it at this point, I just say I convert the credits I have into like a time, like a clock, into like an execution step. And so by this way, I can see that actually I don't have to pay anything more than what I've paid for before already. And so this works really well in the sequential execution, which is also how this technique was first studied. In basically an imperative language, everything would be fine. But of course, we are in a functional language. And so in a functional language, everything is not fine because we can actually pop from the same queue twice. And so if we do this last pop twice, well, the first time it's all fine. We just convert all of the credits into the times, and everything's good. But now, if we pop again, we have to do the exact same reversal again, right? Because the pop operations work on the same queue. There's no work being shared. So actually, I do end up doing a lot more work, and so the second pop actually does cost time linear in the length of the list. And so this is the fundamental problem that motivated Chris Okazaki's work on purely functional data structures, which is that if you work in a persistent setting, every element can transit from the real list to the front list many times. And so if you do n push operations and then you do m pop operations on the exact same version of the list, you actually can get n times m time complexity for this, right? And so we should have some data structures that can work better in a persistent setting. Okay, and so Chris Okazaki also found the solution to how to do this. And the basic idea is to use thunks, because thunks have a really nice property, namely that they're only evaluated once. So this is not completely true in a multi-threaded setting, perhaps, but at least in a single-threaded setting, we can kind of say, well, if you put some expression into a thunk and you'll force it at some point, the first time you force it, you actually have to do all of the work, but then all the forces afterwards just memorize the result of the first time, so you don't have to spend more work. And like this is even true in a persistent setting, so even if there's a bunch of references to your thunks, the work only gets done once. And so if we wanted to make this example work, assuming we had like some magic way of putting our reversal operation into a thunk, well then the first time we force it, we actually spend all of the credits, and we arrive at the result and everything's fine. And then the second time we pop, well, we now look at the same thunk we get the memoized result and we don't have to do any extra work. So if we can somehow change our data structure so that this is possible, we can have the time complexity that we want, even in a persistent setting. And so what I've been doing in my work is kind of trying to take this reasoning and turn it into a DSL that you can use in Haskell to kind of check this kind of reasoning for yourself. And that is something that I call the credit monad. And it has several features. So the first, of course, you need some notion of cost. So you can't really inspect Haskell and ask, like, how long does this expression take? But you have to specify it yourself. So I have this tick constructor that just consumes one time step. Then I have a class called monad lazy. And the idea behind this is that we need to, that of course Haskell is a lazy language. But if you, oh, that's not good. Did I do that? Ah, okay, good. So of course Haskell is a lazy language, but if we're writing a DSL, we actually need to model laziness ourselves, because we have to kind of reason about the laziness kind of from the outside, so we can't use the implicit laziness that's already there. And the way you do this is by having a delay constructor. So delay takes a monadic computation and puts it into a thunk without looking at it. You can also actually just put a value in, so this kind of an already memoized thunk. And then you have a forcing function which takes a thunk and gives you the result of the computation. And the idea is that in the implementation, force, of course, memoizes the result and only runs a thunk once. And then to actually reason about the credits, we'll now combine all of this into the credit monad. And the credit monad has two functions. One is called credit width. So if I'm given a thunk and I'm given some credits, which is a number, I can put those credits onto the thunk. And I also have a function called hasAtLeast, which kind of asserts that a thunk has at least a certain amount of credits and fails otherwise. So let's look at one actual example for how you would use this. And for this, I'll use the implicit queue that Okazaki does. And I have to warn you, it's a bit more complicated than the simple queue I showed at first. But yeah, I think it's one of the simpler examples, maybe. So the way the implicit queue works is first that there's a data type called digit, which is either 0, 1, or 2 elements. And then the queue itself is either empty or it is a deep queue, which means you have 2 digits so that's kind of the front and your real list from the example. And then you have like this middle thing, which is a thunk for another implicit queue. And let's look at an example. So at the topmost, I say I have a deep node with a 1 and a 0 as my digits. And then in the middle, I have a thunk, which will be a push operation, which contains another deep node. And so here, one interesting thing is that the implicit queue that you have in the thunk stores pairs of the initial elements. So in the topmost deep node, I have a 1 in the 1 constructor, and down here I have a 2, 3 pair in the 1 constructor. So every time you kind of go down one level, you end up storing pairs of the elements you had before. So the topmost level stores the actual integers, then you have pairs of ints, pairs of ints. And also if you like push something in, you'll push kind of pairs down. And to make this kind of reasoning work, we have to kind of specify what the thunks look like. And for this, there'll be an invariant. So I'll first take the size from a digit, and then I'll say, if I create a deep node, I have this smart constructor deep, which says that your thunk in the middle has at least as many credits as 2 minus the size of the front plus the size of the rear. So if we look at this push thunk, we can see that the node above it has a 1 element in the front. So the amount of credits I need is 2 minus 1, and so I have 1 credit up there. And let's look at a way I would push into a queue like this. So this is the push function, and I'll walk you through it in an example, so you don't have to read all of it right now. So if I push something into an empty queue, I'll just create a new empty thunk in the middle, and I'll put it into the front Q immediately, or into the front digit. Then if I push another one in, so then I'll just add it to the rear digit, and I'll also put one credit onto empty, but that doesn't matter because empty is not a thunk. And now I'll actually have to do some work because because I can no longer put something into the rear digit, like there's already one element in. So I'll just push the element 2, 3 that I want to insert, I push down into the middle thunk. And so there's a thunk being created here. And I'll also add one credit because the size of the front is 1, so I need to add one credit to the new thunk I've created. All right, so let's say I keep pushing things in. So then the 0 turns into another 1 digit. And I actually put another credit on here, so I now have 2 credits on the middle thunk. And then I'll actually have to force this, which means I'll now take the credits I've accumulated on this thunk to push the tuple 2, 3 into the empty queue in the middle. And of course, there I have to spend 1 tick at the start, so that tick will come out of the credits I have accumulated on the thunk. And then I create a new thunk here, which again, for this queue that has the tuple 2, 3 in it. And I'll again put 1 credit on it. And so this style of reasoning about these lazy data structures is something I call this credit passing style. So the idea is you have these credits on there and you always move credits onto a thunk, and then once you actually evaluate the thunk, you use the credits on the thunk to pay for it. So there's 3 operations here that matter. There's tick, that costs you 1 credit from the thunk that you're currently evaluating, credit width, which transfers 1 credit, and force, which is always free, but it can get stuck if there's not enough credits to pay for it. And this model of reasoning about lazy data structures is something that is, I think, very much inspired by Okazaki's work. So Okazaki has this notion of debit passing style, which was also formalized by Danielson, I think in Popple 2008, and very recently by François Patier, Gounod, Jourdan, and Mevel, also at Popple. Right, so there's this, so now that you understand what amortized complexity is and how to reason about it, let's think about what we can do to actually check that our reasoning is correct. And so, of course, these papers have used proof assistance to verify that it's correct. But this being the Haskell workshop, I want to use Haskell. And for this, I'll use quick check to test probabilistically whether our reasoning is right. And so the first thing I need to do is I need to specify the cost bound. So I need to specify how many credits it should even have. And for this, I'll have this class called a data structure. You can create a data structure, potentially using some laziness. You can also perform an operation on it. So if you have a size for the data structure, an instance, TM, and an operation, you need to specify what happens once you perform this operation on the data structure. And given a size and operation, you can specify what the cost should be. So how many credits do you need to actually perform this? So let's look at this for this example, right? So what the operations I have are pushing and popping. So I can push one element and I'll create a quick check instance that creates a bit more push operations than pops, so that my queues grow over time. And so my implementation will be to create. I just create an empty queue. To perform a push, I update the size by 1, so I add 1 to the size and I perform the push on the queue. And to do a pop, well, I try to pop, and if there's nothing in there, I say oh, the size is 0 now, and I return an empty queue. And otherwise, I see the size is decreased by 1, and I return the results of the pop. And then the cost bound I have is that both push and pop should cost 2 credits each. And with all of this set up, we can now just run quick check on it. So my library takes this data structure implementation I've just given you and generates some quick check tests on it. And if we actually run it, we see that, okay, we've passed all the tests. And that's very good, right? That's what we want. But sometimes, of course, you get your reasoning wrong. And one of the nice things about quick check is that it can give you a counterexample. But actually, in this case, the counterexample is not that useful because we can look at the top bit of the queue. We can see there's a deep constructor. But then there's this thunk in the middle, and it's kind of hard to look into the thunk. So there's not really a lot that QuickCheck can do. And the problem is really in the monad lazy type class I've just introduced, because the delay constructor takes an MA, so a monadic computation in Haskell, which is not really something we can print, because I can't print like an arbitrary Haskell expression. So we need to find some way to defunctionalize this notion of laziness, and this is where, if you've seen my talk on Monday, like this idea of defunctionalizing laziness comes in. And the idea is that I'll just add like a little bit of indirection here. So instead of delaying a computation MA, I specify a type TA, that I'll delay instead. And the idea is that TA can be embedded into the monad MA, but I can specify what T is. In particular, I can use a data constructor for this. And then I've just added this little bit of indirection. So I delay TA, and then in the forcing function, I say, now you have to actually turn the TA into an MA that you can run. So what is an example for this T? So the idea is I create a data constructor for the computation I wanted to run. And so I have to use a GADT for this, but then I can say I have like iPush, which is a kind of a delayed push that I want to have. And the way I implement it is by saying, well, the push is just like corresponds to the push computation that I wanted to do. And then in my code, instead of like delaying the actual computation, push x, y into m, I instead just add this constructor. And so I've added like a little bit of indirection here, but the effect of doing that is that I now have a constructor in my thunks, and I can print a constructor, whereas I could not print the computation beforehand. And with this, I can actually now get some counterexamples. So for this, I modified my implementation to be slightly wrong. So let's say I run QuickCheck now on this wrong implementation. Well, I first push one element in, and I can see, okay, I now have the deep queue with 1 on the front digit. And I can already see that the thunk can now be printed, and I can see the thunk actually is an empty. And then I keep pushing more things in, and at this point, I've actually now created this push computation, which again, I can print on the console. And I also have like the small, so on the arrow, you can see there that I have the small 1, and that is the amount of credits that this thunk has. So if I want to reason about if every thunk has enough credits, I can just look at this terminal and see whether that is true. And so I keep pushing in, and so at some point I even have 2 thunks. So in the big queue, I have this thunk number 4, which corresponds to this push computation, which again has this thunk that corresponds to the inner empty. And at some point, I'll do the pop, and this is actually where I made the mistake in my implementation, and we'll just say like, oh, sorry, I'm out of credits. I tried to evaluate thunk number 4, but I couldn't because there's not enough credits on this thunk. And then you can kind of start thinking about like, well, what did I do wrong probably? But you'll have like an example in front of you and can just draw it on a piece of paper and kind of think about like, yeah, what you're missing. So the results of this are, you can use this credit monad style to analyze almost all data structures of Okazaki's book. So I went through Okazaki's book, I implement all of these things and all of these data structures in my Haskell DSL. And the credit monad was good enough for almost all of them. There's 3 exceptions. One is the banker's queue, which is actually one of the first examples Okazaki's presents, but is, I think, quite tricky to analyze. And for this, I have a more advanced principle that I call credit inheritance, and that you can find in the full paper. There is catenable lists, which are another data structure that Okazaki presents, using another complicated analysis, and that is, I think, something that I'll have to look at in future work. And also there's an implementation of the implicit catenable DAC. I think that's the last data structure in the book. And so there's one case in the concatenation of these where my analysis fails, and I have to investigate why that is. I also looked at finger trees, and so I checked that all of the operations work. And I noticed that the measurement is actually not so easy. So you can't implement measurement just with a smart constructor, but you have to do something smarter. I had one solution. I then emailed Ross Patterson, who had a better solution. And I have all of this written down in the full paper. So thank you.
Hey, questions? Yes.
So in the paper, you give a link to the credit monad package that's
Yes.
on GitHub, presumably.
On Hackage, yes.
On Hackage.
Yes.
So, but this paper doesn't have this kind of artifacts badge on it. So my question is, how much can someone with just the credit monad package on Hackage duplicate the work that you have done here? Because it's like all of the whatever, it's like the testing harness and whatever is probably not, presumably not in the Hackage, right?
No, it is. It is. So I put all the implementations of Okazaki's data structures in the package as well. So you have, I think it's called control monad credit, which is the credit monad, and then it's, I think it's test something, maybe test credit.
So pretty
which is
comprehensive.
Yeah,
pretty
so there's
comprehensive.
all the implementations are in there, and one of the reviewers of this paper also mentioned that they found it easy to use and that they tried it out and like that they could use it for like a simple example.
So you could pretty much reproduce
Yeah,
all the results.
I think so. I think it is. Yeah, and if you have trouble using this, please email me. So I'm very happy to help.
Oh, hi. Yeah, thanks. That was really interesting. I've not seen this implicit queue data structure before, but I'm wondering, does the same, can you apply this reasoning to this these simple queues that you started the presentation with? And if not, is there any reason why you didn't present it with this? Is it more interesting using these implicit queues or something like that?
Yeah, so unfortunately, using laziness is it's a bit tricky. So in particular, the problem is you need to put the thunks in quite early, because you can only start accumulating credit on a thunk once the thunk exists, right? And so even if you start with something like the simple queue, you actually have to do a lot of adjustments to put the thunk in and make sure that it all works correctly. Yeah, so right.
So does this mean that sort of you couldn't use this kind of framework for analyzing the complexity of this, or do you just mean that you would have to, it just wouldn't look so nice?
So this simple queue is just doesn't work in a persistent setting, right? Like you need to change the data structure to add laziness in order for the amortized analysis to be possible at all. And like Okazaki presents a bunch of versions of this, and I've analyzed them, but they are still a lot more complicated than this simple example.
Cool, thank you.
Yeah.
Sorry, is there one?
No, it's fine.
Hey, cool work. I'm curious, when you went and implemented every single data structure from the Okazaki book, did you write any bugs that you found using credit analysis?
Yes, yes. Yes, absolutely. So I mean, the reason this interface looks so nice is that I had to rely on it a lot. So yeah. Oh, sorry. So I mean, like these were bugs I introduced, right? I should say, right? Yeah, but like, yes, yeah, yes.
Okay, so when you're done testing with your DSL thing, right? So I guess you need to translate your testing implementation of a data structure to a production implementation, right? So is that translation like completely mechanical that can be automated, or?
So we're not automating it, but yeah, I think it is relatively straightforward. So I mean, the main way this differs from like a production implementation is that, of course, this is all in a monad where all of the laziness is kind of in this explicit form. So you have to get rid of that, but yeah.
Okay.
I think it's not too hard to do that.
The other question is, so the examples you show, like push and pop, these are basically like unary operations. So do binary operations like the union operation on the map, or like arbitrary or arity operation, do they work the same way, or?
Yeah, I think so it is a lot harder to test them well for two reasons. One is that like I think it's not a good idea to write a quick check generator for like one of your data structures, because then you have to think very hard about like what the invariance of your data structure is, and like I think that is a lot harder than writing a generator for an operation, the way I've done here. So what I do to benchmark something like the merge of two heaps, for example, is that I actually build two of them using these random operations, and then periodically I generate a merge operation that merges them together, which is a bit more indirect, but I think works very well within this testing framework.
Okay, thanks.
So for the previous question about extracting a real program out of this, do you have any, like, have you tried to see if GHC is able to get rid of most of the monad noise if you just interpret everything into the identity monad and funcs into themselves and so on and so forth?
I have not, but yeah, that would be an interesting thing to try. Yeah, I agree.
Any other questions? Okay, let's thank Anton again. So, our next speaker will be talking about another long-standing theme in Haskell research, which is the derivation of programs from their specifications. In particular, Zach will be talking to us about calculating type checkers. Take it away, Zach.
Cool. Thanks. Yeah, hi. So I want to talk to you about something cool, I think, that I've been working on with Patrick Barr and Graham Hutton recently. And yeah, the idea is basically this. It's calculating type checkers. So maybe you've seen some of the work in calculating compilers, calculating other programs. There's this really nice example of you can calculate a fast reverse function from sort of the naive inefficient definition. But don't worry if you've not seen any of this before, because I'm going to explain it all as we go along. This is a functional Perl, and for good reason. I think that the best way of presenting this is a story, really, of how it works. And the reason for this is that hopefully when we get to the end, it's going to be easier to understand, for one thing, but also more satisfying of a conclusion. So yeah, let's get started. Types describe the semantics of your program, right? So the type of your program is going to tell you something about what kind of values it's allowed to evaluate to. And the lack of a type can also tell us something like maybe it's going to fail to evaluate, or maybe we just don't know if it's going to evaluate or not. Type checkers are programs which can tell us such a type if it exists. So hands up if you've written a type checker before. Quite a lot of you. Yeah, I've written a few myself, and you know, the process varies a bit, but it probably looks something a little bit like this. So you're going to start by defining your language, probably write down some typing rules, which are going to involve some various Greek letters and some horizontal lines and this sort of thing. And then you can write your type checker, which is going to be a function, probably. You know, and this is the actual type checker, sure. Ideally, you would then prove some correctness of this type checker. Admittedly, I don't usually do this, but it would be nice. So I guess a bit of an aside, maybe you've seen some of these papers, or maybe you can read them from where you're sitting. There's quite a lot of work in this idea of calculating compilers from specifications. So the idea is that you can start with a semantics of your language, and you can derive a compiler for it mechanically as well as a virtual machine for these semantics. I think this is a really cool area, and we were just sort of wondering, like, can we apply this to type checkers? Can we derive type checkers mechanically via calculation? And yes, you can. You can actually do that. And so in this talk, I'm going to explain our techniques for doing this, and how maybe you can apply these to your own type checker needs. So yeah, to set this up, you need a language. For the purposes of this presentation, I'm just going to use a really simple language. We've got values, we have addition, and we have conditionals. This is like a if condition, if true, else false sort of thing. So it has 3 expressions with it. We need to describe how to evaluate this language. Again, it's really not hard for this language. It's just a sort of a compositional semantics that we're writing down here. So to evaluate an addition, you evaluate the subterms, and then you add them together. So the third thing we need is the equation that we're solving. And so we want to kind of say, what would it mean to have a type checker for this language? A natural thing that you might want to write down here is this one. So you see on the left-hand side, we are evaluating the expression E and then taking the type of this value. Tval takes the type of value. And on the other side, we're just applying our type checker, which is called texp. And this is an equation with 3 unknowns. I'm going to have all the unknowns in italics just to make it clear. Tval, texp, which is the type checker, and also the set of types themselves. So that's 3 unknowns, 1 equation, which is not necessarily ideal. But actually, we can have a look at 2 of these to start with. So, right, what are the types? Quite a natural thing to do is to just say that each value constructor gets its own type. So here we're going to have integers, booleans, and this error type. And then this gives, again, a very natural definition for our tval function. It's worth noting that you can actually calculate these things as well. I'm going to skip over those details, though, because it's kind of boring and obvious. But it is also worth noting that we can, if we need to, refine these later during the calculation. So this is sort of just a starting point. But the great thing is that this leaves us with just 1 unknown, which is this tx, which is our type checker, which is what we want to calculate. You actually can't solve this, though. Unfortunately, it's too strong of an equation. Some of you might have realized this already. The reason relates to this question. And okay, so what is the type of this program here? If true, then 5, else false. In most languages, this is going to be a type error because the 2 branches have different types. But our equation said that the type checker has to give us the same type as evaluating it and then taking the type of that value. In this case, the value is 5, its type is an integer. The type checker would have to look at the values. It would have to do evaluation, and this is sort of no longer a type checker, really. We don't want this behavior. You can, therefore, really think of a type checker as more of a partial function. It's allowed to fail. It's allowed to say, I don't know, if it doesn't know. And the natural way to do this in Haskell probably is using the maybe monad. This actually works. So, we could reframe the specification using this type for our type checker. But the problem is that now we're working in this monad, and it makes the equation a bit clunky. It makes the calculations a bit more long-winded. It's not very nice. But there is another way to do this, actually, which is a bit more elegant, I think. And that is that we place our types in a partial order. So we say that any 2 types are incomparable except with error. And error is the smallest type in this order. So error is less than anything else. And in this way, you can sort of look at this as an information ordering, right? So if one type is less than another type, it is less specified than that type. It contains less information in some way, and this lets us write a slightly different specification as an inequality rather than an equation. So here you can sort of see that the type checker, it might give the type that we're looking for, but it's also allowed to give something which is less specified. In this initial set of types, that's just going to be error, but you could look at more complicated type systems as well. So with that, we can try and start these calculations. And I like to say it's sort of just like in maths. It's a bit of a lie. But it's sort of just like in maths. Essentially what we're doing is we're trying to solve this inequality by induction, specifically what we call constructive induction, which is we're solving it, but while we're solving it, we're allowed to introduce definitions, defining clauses of this tx function, or of any unknown really, in order to make the proof go through. So let's start off in very much the same way as sort of the standard compiler calculation literature really. We're going to start on one side of the equation. I'm going to do the conditional case here with if, but same goes with any of them really. And we want to transform this into the right-hand side of the equation by potentially applying induction and also introducing definitions of our type checker. So we can firstly apply some definitions here. We know how a val is defined, and this gives us this term here. We really want to be applying induction, and these calculations are primarily driven by this desire to apply induction. In order to do this, we need a t-val of eval of something, right? We need t-val and eval touching because this is our induction hypothesis. It's that t-val of eval is greater than tx. But we don't have this. But what we can do is we can just sort of postulate this function, right? We can just say, imagine we have some function. I'm going to suggestively call it cond prime. And I'm just going to say that this function is exactly what we need to get this term in the form where we have lots of t-vals and evals next to each other, which is very convenient. You can see that this step we're doing, actually this is a less than the previous term. But this is okay because remember our specification is also defined as an inequality. So all good so far. Now we can apply our induction hypothesis 3 times on x, y, and z under the condition that this cond prime, which we've yet to define, is monotonic. And that's just because, again, we're in this partial, we need to apply it inside the function's arguments. But now we're at a point where we can just sort of say, like, okay, this is a definition of tx at if x, y, z. And by doing this, we find ourselves at the right-hand side of the equation. And so this has given us one defining clause for our function, for our type checker. And we can also, well, we have to calculate this cond prime. I won't show you the calculations here. They're not that hard. And we get this. And this is probably what you'd expect, right? This is if the 2 branches have the same type, then the conditional has that type. Otherwise, it is a type error. And like, okay, this is maybe not entirely satisfying. I'm not that happy with this for 3 reasons. Firstly, it feels a little bit weird to have just said, okay, imagine we have this cond prime which has this property. There's sort of some creativity there, and we don't want to be clever, ideally. And actually, the second problem here is a little bit similar. It's during the calculation of cond prime, which I haven't shown you, we have to introduce a lemma to make this particular calculation go through as well. And it's from this lemma that we get the body here, which is if the 2 types are the same, it's that type, otherwise it's an error. And again, we don't want to think about this. We don't want to be clever. We don't want to be creative. We just want this to come for free, right? And finally, there's this annoying sort of niggly bit of we have to prove monotonicity of cond prime, and same goes for add prime when we do the add case, and this is annoying. And again, it's not a hard proof, but it's not totally trivial. It's not free. So in the rest of the talk, I'm going to explain how we can solve each 3 of these problems in sort of a more elegant way. So let's come back to our semantics. And as I mentioned, these are compositional semantics. This is it's a fold, basically. It's we evaluate the subterms and then throw these into a function that does something with them in a non-recursive way in and of itself. As a result, we can write it as a fold. And actually, we can write the type checker as a fold as well. The type checker that we came up with in the end does happen to be a fold. I say happen to be, okay. It's not just happening to be, but cool. Here's our specification again at the bottom. And let me just substitute these definitions in, right? So we're going to write this in terms of the folds instead. Maybe this reminds you of something. Maybe not, but maybe. Let me, again, suggestively put something on the screen. This is the fold fusion law. In Haskell, you can fuse a function into a fold by coming up with some new folding operators subject to certain conditions. These are sort of like distributivity conditions, you could say. These are them. And actually, you can generalize this to a partial order, so to an inequality rather than an equal sign here, under this condition that f prime, this folding operator, this new one, is monotonic. And of course, we can also generalize this from lists to any type, well, any algebraic data type, right? Any inductively defined type. For example, our expression type. And maybe you can see it now. This is exactly our specification. If we substitute t-val for h and also for this val prime operator, it's exactly our specification. And the great thing here is we now know that if we can find a con prime that satisfies, well, okay, there are five conditions here. Any con prime that satisfies these 5 conditions also satisfies our specification. So I guess you can look at this as, we've sort of divided the problem up a little bit, and we can look at these separately, which is great. But more importantly, for me at least, this has fixed our first problem. We now know where cond prime came from. It came from the fact that this is just fold fusion. So we can come back to calculating things. Let's try and calculate this cond prime from this when I say second, it's actually the first one's a bit boring. So second condition. This is, again, the definition of this cond operator. This is defining the semantics of these conditionals. And it's defined by pattern matching on this first argument. So it really only makes sense that we're going to solve it by induction on this same argument, right? So let's do that. On the same cases, we can start with this case where the condition is this is true. And the goal here really is that we're going to start with this inequality that we're trying to solve, and we're going to try and find some definition of cond prime which implies that this is true. So firstly, we can just substitute our x in, of course, and we know some definitions, so we can apply the definitions of cond and of t-val. And this is kind of looking like a definition already, in a way, by pattern matching. What we can do actually is we can make this strengthening step. So this is now a reverse implication. So this inequality implies the one above it. And what we've done is we said, I don't really care that I have a t-val z and a t-val y. Let's just say, okay, what if this is true for any t and any t prime? The motivation for doing this is that this just looks even more like an actual defining clause for this cond prime. Like, say you flipped around this inequality and changed it for an equals, this is a defining clause. Okay, cool. And actually, this pretty much goes exactly the same for all of the other cases that we look at for x. So here's the integer case. I won't show all of them, but here's the integer case. It really is exactly the same. We substitute x in, we apply cond and t-val, and then we make this same strengthening step again. So what we're left with is 4 inequalities. We still don't have a definition but it's looking a lot closer to one, perhaps. And actually, these are sufficient, right? You know, again, if we can write down a definition of con prime that satisfies these constraints, we have a definition of con prime. We can make some transformations to begin with, actually, without really thinking too much at all. Firstly, we can change, you see these inequalities here for equal sign, because if something is less than error, it is equal to error. These two are now defining clauses, right? But we can't use the first two as defining clauses yet because the patterns will be overlapping. You see the right-hand side on each of these is exactly the same. But again, we're working in a partial order. In fact, we're working in a partial order with a bottom, and therefore we can use the greatest lower bound. And this lets us combine these two inequalities at the top into this one inequality at the bottom. And this is actually just the definition of the greatest lower bound, right? It's, you know, this constraint here is equivalent to the two constraints at the top. So we now have 3 constraints rather than 4, and this is great because this lets us literally just write down the best possible definition in some sense, the sort of largest possible definition satisfying these 3 constraints, and we just do that by changing all of the inequalities for equal signs. And also we can combine the last two because they both have error. Okay, cool. This is now our definition of con prime, this operator which finds the type of a conditional. And actually this is functionally identical to what we had before when we did the whole calculations in the previous way, because this definition of the greatest lower bound, you can just read off from the graph that we had of the ordering that it is, if the types are the same, it's just one of these types, and otherwise it's error because that's the bottom value. But the great thing is that this time we didn't have to be clever. We didn't have to sort of think like, oh, okay, let's write down an if here, and let's say like, okay, let's put this t equals t prime here, and you know, it was completely natural. It fell out of the calculations, and this solves our second problem, which was that we didn't want to think of lemmas in general, this one specifically. Great. Monotonicity is still kind of annoying though. So, you know, 2 out of 3 so far, but actually this monotonicity proof that we have to do for each of these operators takes more time than I would like. So let's have a look at that. And sort of, let's, I guess, take a bit of a roundabout way to looking at this. If we come back to these constraints that we calculated in the previous step, you remember after doing this, this sort of reverse implication weakening, strengthening, not weakening, sorry, step, we get these 4 constraints, and I just want to write down a function that satisfies these. It doesn't feel like it should be that hard, right? I just want to say like, okay, if the first argument of my conditional is an int, then just give me an error. Otherwise, like, you know, don't worry about it. Just ignore this clause, ignore this case. It doesn't matter. And equally, if it's an error, give me an error. If it's a Boolean, I want it to give me t and also t prime. And but you know, otherwise, ignore it. Don't worry about this case. And like, you know, I'm trying to write this, but I can't quite write it because Haskell doesn't let me. I have to put something where these question marks are. Let's call these clauses, right? And I'm combining these with the greatest lower bound. Reason being, if I get an error in one of these, then I want the whole thing to be an error. Simple as that, really. Yeah, but we can't write this down because we don't have a type that we can write here. We want something that's sort of invisible to the greatest lower bound. But yeah, the great thing is that we actually, you know, we have control over our partial order. So we can just say, introduce a type that is invisible to the greatest lower bound, and actually this is the top type. Top is greater than anything, So the greatest lower bound of top and anything else is anything else. And this lets us write this definition here totally mechanically. There's no thinking at all, after changing the ordering. This is a valid definition. This satisfies the constraints. This is con prime. And, right, it looks a bit weird. The calculations were a lot nicer. They were a lot cleaner. Well, there were less of them. But yeah, we can introduce some syntax as well. If we define this sort of wobbly arrow thing to mean precisely this, if something else top, it looks a bit nicer. We can also combine the last two together using the greatest lower bound because they had the same condition on the left-hand side. Great. This doesn't really answer the question about monotonicity, though. So why am I talking about this? So here is an observation. We can actually replace this double equals here with a less than. Why can we do this? Well, it still satisfies the same constraints. The reason is maybe subtle. It's not totally obvious in this presentation. It comes from actually the fact that we're sort of assuming the monotonicity of con prime. Don't worry, that's actually not a circular argument, but I promise. But this is cool because, for one thing, it lets us simplify the definition a bit. Okay, so these top two cases can be collapsed because if something is less than error, then it's also less than int, because error is less than int. So we can remove that case. And the really cool thing about writing it in this way, with this less than rather than this equals, is that we have monotonicity now actually for free. And so I claim that any function built up in this way using the greatest lower bound and this wobbly arrow is monotonic. For some intuition as to why this is the case, think of these clauses, so these sort of wobbly arrow clauses, as firing or not firing based on their condition. So for this to be monotonic, that means that if I have an S prime smaller than my S, then my con prime applied to that S prime should be less than applied to S. And you can see here that if I take an S prime which is smaller than my S, then at least the same clauses are going to fire due to transitivity. And the thing is that we are using the greatest lower bound to combine together all of these clauses, and that means that we're going to have at most the same type, but it could be less than it. So this is less than or equal to previous type, therefore it's monotonic. Of course, that's not a formal proof. There is a formal proof, but that's not it. But yeah, okay, the great thing is that all of our functions, all of our type checking folding operators, add prime, con prime, anything else we might add in the future, are constructed exactly in this way. Therefore, they're all monotonic automatically without having to do any additional calculations or proofs. So what we're left with is a little bit of a strange-looking type checker. I've certainly not seen one written quite like this before. But once you get used to this sort of syntax, actually, it's quite natural to read, I think. So if you look at this second one here, this add prime, which I've not shown you yet, but this is what you end up with. You can kind of read this really as, if both arguments could be an integer, then the addition of them could be an integer. That's the first clause. On the other hand, if either of the arguments could be a Boolean, then the result is a type error. And I say is. Technically speaking, this is could be a type error. But if something can be a type error, then it is a type error. I think this is called Murphy's law or Sod's law or something like that. So, yeah, I mean, this is quite a cool approach. I think this gives us the monotonicity for free, which we needed to apply fold fusion to get our specification. We've got a few minutes. Yeah, so just to kind of take a step back and have a look at what we've done. We've sort of taken these, I guess, fairly standard compiler calculation techniques, and we've applied these to this new setting, which is type checkers. So we can compute a type checker from an untyped language and its semantics. Using these techniques sort of in the sort of plain standard way, we weren't totally satisfied. The calculations felt a little bit clunky, too creative, and we don't like being creative. It was a little bit unclear where some of the steps came from. And also the monotonicity issue, which is really annoying. And we fixed these things basically by looking at the algebraic structure of the problem that we had here. You know, the fact that our specification really is fold fusion. And also looking at this partial order that we had to introduce in order to generalize the sort of standard techniques to our type checking situation anyway. And yeah, this has given us a really nice technique here, I think, that you can apply to various languages. Yes, in conclusion, this is a nice principled way to derive type checkers. I've shown you it on really a very simple language here. We only have 3 like AST structures, right? There's not much to it. In the paper, we do look at some slightly richer type systems with some subtyping and some you know, slightly more complicated languages. Also, all of the proofs, all of the main results are formalized in Agda. So when I've said something like, you know, trust me on this one, or this is not circular reasoning, I promise, this is why it's actually not circular reasoning. These techniques do apply more generally to what I've shown you here, as I say. So subtyping, for one. In some upcoming work, we also have looked at calculating typing rules rather than type checkers in somewhat a similar way. I think a very interesting way of looking at this as well, but typing rules rather than checkers, so not a function, but a relation. And I think that there's a lot of cool stuff, really, that you can look at in this area. Yes, I think, though, that's all I have for you for now anyway. Thanks for listening.
If I may, I'd like to ask a question.
Yeah, of course.
When you have these inequalities, always on the right-hand side is where your unknown sits, right, usually.
Where are we looking?
Like any of the specs that you have. Fund prime, when you're trying to derive that.
These ones?
It's on the right-hand side, right?
Sure.
And you needed to show, you needed to pick the best possible one in some sense, right? So there was still a little bit of creativity, it seems, because you had to, you couldn't just return error all the time,
Yeah.
right?
Yeah, this is a really good point. So yeah, it is true that another valid type checker is just this function con prime underscore 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 equals error. One nice thing about the calculational approach actually is that as you go through these calculations, it exposes very clearly where your choices are. So it lets you come up with almost what you want, but it nudges you in the right direction of, you know, these are the possible things you could write down. But secondly, where is it? So here, where we have this inequality at the top, which is con prime bool t prime is less than t greater slow bound t prime. So what we do is we just turn this into an equals, and this is the greatest possible because any other thing that satisfies this would have to be less than that. So does that?
Yeah, so I was just wondering though, in a more complicated type system, could it be such that you may not pick the best possible one without realizing that you can do so? Like here, it's very obvious that you should just turn the inequality into an equal sign.
Yeah.
But maybe, I don't know, when I finished writing a type checker for a complicated language, that I have picked the best possible solution to those inequalities.
Yeah, that's a really good point. I think I wouldn't be able to sort of say 100% I've done the calculations and I know that this is the best one. But it's actually worth pointing out that technically speaking, this isn't even the best one. So because we do actually have almost permission to add new types. And so what we could have done is added some sort of subtyping or some sort of dependent typing of, in this conditional, rather than giving a type error, we give like a union type. So I guess the answer maybe is not a very satisfying one, but it's that there's a lot of flexibility. The best possible definition, I suppose, would be to always just introduce a new type for every possible computation that you have. But that is a bit of a trivial solution as well. So I guess you always want something somewhere in the middle based on your needs.
Once you introduce top, don't you need to prove that top is never the answer from the type checker?
Oh, yes, good question, sorry. I meant to mention that actually. No, it's a really good point. So you don't actually need to prove that, but it never will be the answer. And the reason is that if I come back to my specification, where's my specification? That'll do. So we're saying that the type checker is always less than the type of the value of evaluating it. And we know that no value has this type top, which means that if we're less than the type of our value, we're always going to be sort of below top. And since our type checker satisfies this specification, then that does suffice as a proof of this. Does that help?
That was a really fun story.
Thanks.
I want to tell you a different fun story related to the fact that Liam pointed out that you could just pick error all the time.
Mm-hmm.
So when I was writing my textbook, Programming Language Foundations in AGA, I was writing a type checker.
Mm-hmm.
And I started by writing one and proving if it gives you a type, the type satisfies the type rules. It's sound. And I did all that, and I just had to, I could have just always said false, and that would satisfy the specification. And then it hit me, oh wait, I can do a decision procedure. And then instead of arbitrarily making up error messages, the error message was a proof that this thing could not have this type. So that's a different way of approaching this than you did. It's not calculational, it proves the result sound, but this idea of, that hadn't occurred to me before, that what you want your type checker to be is a decision procedure for the typing relation is a neat idea, and it deals with this fact that it won't let you say it has no type unless you can prove it has no type, and then a proof it has no type becomes your error message, which is sort of cool. So that's just an alternate method. It'd be cool if you could combine that with your technique. I don't know if that follows or not, but I want to match your nice story with another nice story to maybe give a next place to go.
Yeah, thanks. That's a really nice idea, actually. I'd not thought about that so much before. I guess not to start a discussion in the Q&A time, but so how does this actually deal with not just giving error? Because couldn't I just, I mean, in this case with my conditional, if the branches have a different type, I sort of do want to give an error.
Well, the type rules in this case tell you that it only has a type if both branches have a type.
Oh, so is this sort of, you have typing rules and then...
In this case, I'm given the typing rules, right? I'm not deriving them.
Yeah. Yeah, it's possible that that could be really interesting on this further work that I was mentioning, where we do come to calculate typing rules rather than type checkers, because then we're interested after that in deriving a type checker from these rules. I suspect it could come in there. Yeah, thank you.
Thanks. Excuse me if you already answered this, but does this scale nicely to deal with, I don't know, functions and function calls and lambdas and recursion? So
yes.
I read the paper, but none of those words are mentioned in the paper, so I wondered.
Thanks. Good question. Yes. So this exact technique does work with lambdas. We actually, unfortunately, had to take it out of the paper due to space constraints and reviewer comments. But I'd be really happy to show you how
So there's
that
an
works.
appendix somewhere.
There isn't, but I should put it somewhere.
You should
In
put
fact,
it somewhere,
I
yeah.
should put it somewhere.
The reason I was wondering is because that your specification says, well, just evaluate the program. The spec is evaluate, compute its value and then take its type, right? But if it's a program that runs forever or that runs a very long time, that doesn't seem very feasible as a specification. So I was wondering how could that possibly work?
Yeah, so that is a really good point. So, and actually this is why we moved on to calculating typing rules later on. So when we calculate a type checker with lambda terms using this particular technique, we had to limit the source language to just only terminating lambdas, in which I think is a little bit unfortunate. What we essentially said is that we only have, so the argument to a lambda can only be like a value rather than another lambda itself, so which is admittedly limited. Looking at calculating typing rules rather than calculating type checkers is, the techniques they're similar, but it does get around this problem quite nicely. So hopefully that's
Okay,
gonna
that might be
appear
better.
soon.
Yeah, because you don't want to take a technique that has a sort of fixed ceiling.
Yeah.
Just as great when Simon said, yes, publish all the work.
Yeah, I will. Thank you.
Yeah. Jinyoung Zhang from McGill University. I think this approach has one, in a sense, maintenance problem, in the sense that if you extend your type system, then you need to deal with the coverage problem, because you don't know whether your current rules are actually covering or not. How do you deal with that kind of problem in general?
Wait, sorry, we don't know if our rules are what was that, sorry? I didn't quite catch the last sentence.
Sorry?
Sorry, I didn't quite catch the last sentence. We don't know if our rules are what?
Like whether you covered all possible types for example, for the cone prime. So, yeah.
Right, so that really we just get by here. We just, so it's essentially we do an exhaustive, so here we're doing the case of true booleans. We also do the false booleans, we also do integers. Essentially we just run this calculation for every value constructor in our language. So we have an exhaustive proof here. Does that sort of answer the question?
I mean, the cone itself is like defined in a covering way, exhaustive way, but like if you define the cone prime in the way you defined it, then when we extend cone, we might forget to extend cone prime. So in that case,
Right. If you redefine cond, you would have to do the calculations again, at least for the clauses that you've changed. Similarly, if you added a new value, you would have to then run the calculations for this new value constructor, but you wouldn't have to do the calculations again for everything else. So I guess it's something you have to be careful. There's no it won't tell you because it's you're just writing stuff down on a bit of paper. But yeah, you do have to be careful about that. Does that?
Hi. Have you thought about extending this approach to bidirectional typing?
Yes. Wow. Great question. Yes, we have. In fact, so that's basically my plan when I get back to Nottingham. Thank you. Thanks for that.
Hi. Have you considered the connections to abstract interpretation? Because it seems like types can be considered an abstract interpretation, and monotonicity, having a lattice, these are all things that you might expect of your abstract domain, and it does seem like that's very similar to what you're doing in some way.
Yeah, absolutely. Good question as well. So this is very much linked to abstract interpretation. I'm not an abstract interpretation expert, but there is a link there. And in fact, there's a paper by, I believe, Kuso and Kuso, about calculating abstract interpretations, which I, to be honest with you, could not really make it through to the end. But it seems very interesting. I think that there's a lot of, I think that there's some very deep links here which are worth looking at, and I need to read more about, basically.
I think there is a paper also by Kuso, somebody related, on viewing abstract type inference as abstract interpretation.
Yeah.
So that's a great idea that has to be looked at.
Yeah. Thank you. Yeah, I need to check these things out. I think there must be a lot there.
So in one of your earlier slides, you have the expression "if true, then 5 else false," and that does not type check, or rather that produces the error type, because the greatest lower bound of int and bool is error. But you could argue that you can specialize the if expression to produce some type of int and bool. So have you looked into that? Because naturally it seems that, if you have an if expression, you really should have a sum type. And so rather than the greatest lower bound, which is like some kind of a lattice theoretic meet of these two types, you really should have a join.
Yeah, absolutely. Absolutely. And maybe this was another thing that we had to remove from the paper. Yeah, absolutely you can do this, and absolutely it works. And actually this comes back to what I was talking about a little bit earlier, sorry. Anyway, I'll find the slide. But it was where I say that this is the initial set of types, but we can refine this during calculations. And a refinement that is often very useful to make is exactly this thing, is sort of introducing sum types or introducing so various subtyping rules. And yeah, absolutely, this can fall very naturally out of the calculation as well, if you keep in mind during the calculations that you're allowed to modify this set of types. And this comes back to the earlier question of how do you know that you have sort of the most general type system? And the answer is you have the most general type system with respect to what you're allowing yourself to do during the calculations. So, yeah.
All right, let's thank Zach once again. I believe it's now time for lunch.
Test, test.
Chris Cardwell. Hello, I'm Simon. You work for Well Typed. Right.
I'm following you today.
Did we meet before?
We have. We met in Tokyo.
Some while ago.
It's been a while.
Yes, it's been a while. Yeah. Do you live in Tokyo? No.
Close by.
Oh, right. Right, so explain why we don't meet very much then.
There's 2 more chairs for the adventurers. Okay. I think we ought to get started though. Yeah. All ready? Okay. It is my honor to introduce Simon Peyton-Jones today for the first keynote of the Haskell Symposium. Simon probably doesn't need an introduction. I'll try anyway. Simon, since his time at Glasgow and then at Microsoft and now at Epic, has been the strength behind the GHC compiler that probably everybody here uses. He's also been, a shepherd for this community, has helped us be better selves and better researchers. And again, it's an honor to be presenting, Simon. Please take it away and tell us everything about drawing points.
Okay, thank you. All right, thank you. Thank you for doing me the honor of coming. There is still a spare chair here. There's nothing wrong with it. It's a perfectly good chair. In the beginning, there was Rabbit. I was 20 years old when this paper came out. This is Guy Steele's thesis. Important part of his thesis was him saying, we should compile using continuation parsing style. Look at it, this was really very early 1978, the real meat of the compilation process. Continuation parsing style, a language isomorphic to scheme with the property to interpret it requires no control stack or unbounded temporary storage. The importance of these properties cannot be overemphasized. Well, I was sort of brought up on a diet of lambda the ultimate, so I thought, the real meat cannot be this is obviously the way to go. A little bit later, quite a lot later, actually it's 14 years later, Andrew Appel's book, Compiling with Continuations, came out. This is also, a revelation. Andrew is also a deity in my firmament. And he's too said, don't use direct style in the compilation, just use CPS. Everything will be great. So by then I'd started to build GHC. And GHC was a direct style compiler, right? Everyone sort of wrote papers about how it worked. So I was feeling quite embarrassed by now, right? All these famous people had been saying for years, use CPS style for your compilation. So why didn't I just adopt CPS style right away? Well, there were some reasons. You may think them good or bad, like CPS rather fixes the order of evaluation. That's part of the point. But in a compiler for a lazy language, you want to be a bit flexible about order of evaluation. You might want to float lets out or inwards, imposing an order of evaluation for everything. Not so good. And also, it's not really so good for certain kinds of transformation. Common sub-expression elimination isn't so easy. And inside GHC, we also wanted to do a lot of using rewrite rules to rewrite one term into another. And it's very convenient to have rules that say, f of g of x rewrites to h of x. By the time you encode this in CPS, it's not quite as easy for the compiler to spot that composition. Direct style is very convenient for that. So the reason for my embarrassment, therefore, was not entirely that I was lazy. It was that, well, of course, it was a lazy language, but that was it. Okay. So then, to my great relief, Cormac Flanagan and his colleagues wrote a paper that essentially said, you don't need CPS at all. Just use administrative normal form. I'm abbreviating this paper, which is a very interesting paper. This is 1993 by now, so I breathed a sigh of relief and thought, fantastic. No need to use CPS after all. Andrew and Guy Steele were wrong. It's all fine, I just use ANF. But then, sadly, my very dear friend and colleague, Andrew Kennedy, treacherously betrayed me by producing this paper that said, no, ANF's no good. I mean, there's a lot of title engineering going on in the continuations world. Compiler with continuations continued, another nice title, don't you think? So, ICFP 2007. So he said, actually, there's juice that you can't get using the sort of Cormac Flanagan's ANF story. So the story of this talk, which is really from our paper in PLDI 2014, is, and I'll tell you how this collaboration came about, is to say, actually, this idea of join points that I'm going to tell you about today is the sort of, the power that says, no, Andrew Kennedy's wrong. We can actually do everything in direct style with the advantages that have, and not lose, I claim, anything or maybe anything much. There's going to be a challenge for you at the end to prove me wrong. Okay, so how did this paper came about? It came about at ICFP because Zaina Ariola approached me quietly and said, she sat down to lunch with me and said, Simon, you use the lambda calculus as your intermediate language for GHC, and you're very proud about it. You give talks about using this nice small system F as an intermediate language. But she said, that is the term language for a logic that is, it comes from natural deduction, right? It's the appropriate term language for natural deduction. She said, I spend my life thinking about sequent logic, and the natural calculus for that, the term language for that, is sequent calculus. So maybe sequent calculus would be a better intermediate language. So being a broad-minded fellow, I said, well, of course, Zaina, that could be. Let's see if we can understand it. And then I need to understand sequent calculus. And then I think, oh, man, there's lots of turnstiles and stuff happening to the left and stuff happening to the right. So it's a long period in which Zaina and Paul and Luke patiently educated me in what this sort of bottom row was. Luke, are you here? He is there in the corner, right. So Paul, sadly, is co-scheduled against this talk. He is giving a talk somewhere else. Right now, alas. Now then, so we sort of understood more or less what a sequent calculus intermediate language for GHC might look like, and Luke then implemented a pass in GHC that took core, this lambda calculus language, turned it into sequence calculus, then he optimized it, which is the bit that was going to be allegedly easier, and then turned it back into core again. That was quite a lot of work. And as it turned out, tell me if I'm misrepresenting, Luke. As it turned out, it was quite a lot of work and really wasn't better. Right? The sequent calculus, it had more data constructors in the language. There was quite a bit more hoo-ha to push things around, and we couldn't achieve any results. We couldn't achieve in direct style. So that was a little bit disappointing, right? And so Luke had his hair falling out by then. Fortunately, it's regrown, I'm happy to say. By the way, let me say that this is a this is a sort of tutorial kind of talk. It's really a bit of a retrospective. I would love to have comments and questions as we go along rather than saving them up respectfully till the end. It would make me feel that you were actually listening rather than reading your email. So please do. Okay, so then having had this sort of slightly disappointing experience, we didn't give up. So Zaina and Luke and Paul and I had a lot of interaction. They very patiently helped me, and finally we emerged with this idea of modifying core in a very small way to add join points. And that turned, so it was a sort of like a principled extension in the end. And that's what I'm going to tell you about today. So the payoff is that we're going to get a small change to a direct style compiler that gives you access to all of the good things that we were hoping to get from the bottom line, okay? And it worked so well that when Ning said, would I give this talk? I thought maybe, even though this is talking about stuff we originally published a paper about 8 years ago, thought if you're building a compiler of almost any kind in direct style, you really ought to know about join points. It's like a super useful, super easy thing. So that's my hope, is to just share the love today. Okay? All right. Now, so a little bit of background then. So which probably most of you know. So Haskell is a very, very big language. It has, lots and lots of, its abstract syntax has lots of different constructors. So we type check that language and desugar it into this very small core language, and that's what we're going to be talking about today. And here is GHC's core language, more or less as it is today. And it really is quite small. I know I'm a biased witness, but I'm quite proud of the fact that 30 years on in GHC, it still only has variables, literals, applications, lambdas, let, case, type. What's type for? Type's for type arguments. It's a system F language, so you've got to have the argument of a function can be a type. And then casts and coercions I'm not going to talk about today. They're all to do with the new types and type families. Okay? So that's terms, which here are expers. What are types? Well, they're just type variables, literals, applications, type constructor applications, things like list of T. That's just arrow. And this is a for all type. So it's quite a small language. The coercion language is rather bigger, but we're not going to discuss it today. But also, in the optimizer, you never look at coercions. You build coercions. They're like proofs that you need to check that you haven't made a mistake. But the optimizer is never guided by the structure of a coercion. So the structure of this data type is not very interesting. We don't have lots of passes in GHC that look at the structure of coercions. Lots that look at the structure of expressions and look at the structure of types. And finally, this bind, this let here has a bind. What's in a bind? Either it's non-recursive or it's a recursive with a bunch of variable right-hand side pairs, okay? And every binder, like these IDs here, is, maybe that should be a var. It's ID is a synonym for bar. It's just a pair of a name and a type, or if it's a type variable, a name and a kind, right? So every binder has its type with it. So that's it. That's it for core. And that's done us for 30 years, and it's still working quite well. Now, so that's the language we're going to use. I'm going to show you now a bit about the optimizations that we want to get access to using this join point stuff. So here is the place that I started, in 1990 when I was building GHC. Here's a function not null that's just not of null of x's, and I'd like to compile that, optimize it. So what is it? Well, so here's the definition of null and not, right? They're just very simple expressions. One, null says, is the list empty, and not inverts a Boolean. So, so what have I done here? I've just inlined not, haven't I? All right, so case null of x's, that was easy enough. And now here I've inlined null. So now I've got a case, scrutinizing a case. Okay, so the outer case black, that's like a crocodile that's trying to eat the inner red case. And so what would I like to do? Well, really, I want to push that outer case to consume the arms of the inner case. So the outer case is still up here, so that I've just moved the same thing up. The black case, here, I've just moved it into the branches of the red case. This is really important that you understand this slide. There's nothing complicated going on here, but if you get lost here, you will be very lost in everything else, okay? So just tell me if you get lost. So here, what have I done? That outer black case, that's a copy of the black case that's scrutinizing that true, right, the first arm. And then I've copied the alternatives into the branch. And here I've copied the whole thing again, scrutinizing false. So far, so good? Easy? Yeah? Fine. So now, of course, I can simplify this case true, and I get, this is, of course, the code I wanted to get in the first place. I've just fused away the intermediate Boolean, all right? We have to do this. This is, you know, the primary way that GHC optimizes things is to inline and then do lots of case and cancelling known constructors. Fine. It's not just case expressions that can consume these case expressions. It's also other strict contexts. Like, here's a case that's consumed by an application, right? So here, you could think of that's a function applied to arg1 and arg2. So the application to arg1 and 2 is like the continuation. Oh, this outer black case, that's like the continuation, what to do after the inner red case. Here, these arg1 and arg2, I like to push them into the branches. And it happens the other way around. If you've got a strict function applied to a case, I might like to move that strict function inside and apply it to both branches, all right? So pretty much any strict evaluation context, we want to do this kind of thing on, right? Now, there's a little worry that you might have that I've talked about duplicating stuff, and you might worry about duplicating arbitrary amounts of code. So here's, supposing the black case, the outer one, the outer crocodile, had big arms. Crocodile with big arms, right? Here, big 1 and big 2. Then I don't want to duplicate big 1 and big 2. Just slow my compiler down. So what can I do? What can I do? Let. Yeah, let. We could just let bind big 1 and big 2, right? That's what let is for. And now then I can jump to J1. It's a lazy language, so I didn't really need these units. But I thought there might be some call-by-value folk in the audience, so I thought I'd sort of try to avoid, you know, making you sort of feel too uneasy. Okay, so this is pretty obvious thing to do, right? So we're going, but in order to make our continuation duplicable without blowing up code, we're just going to let bind these little J's. At the moment, they're little J's. I'm calling them join points, but they're just ordinary let bindings so far. Okay. Now then, the other, so having done that, now I do my case blah, 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 case blah, blah, blah. Now, look, when I've got to this point, oh, J1 is called just once. So I can inline J1, right? However big it is, that's not code duplicative, but I sort of discover that later. So the first thing I do is I let bind it just in case. Then I simplify away, and then if it turns out it's only used once, I can inline again, right? So, fine. Now, the other point to make here, which is that the same idea generalizes completely smoothly to data constructors that bind terms, bind term variables, or that bind existential types, or that bind bind equality coercions. So here's an example that's just a term. So here now I've got a case in which I've got just x. And big 1 here mentions x. What should I do? Of course, all I have to do is to make j have x as a parameter. Simple, right? And it will be fine if this data constructor had a type variable as its argument was binding an existential. That would be fine. I could pass that to j as well. Then j becomes a polymorphic function. No problem. This is system F, okay? So this is one of these times. Sometimes you think, oh, here's a little problem, and it ought to be easy, but it's really hard. This time, there's a little problem, and it ought to be easy, and it is easy. That's always a relief, and on this occasion it was. Fine. So then this is the next thing I'd really like you to remember. Probably all of you have spotted this, but these J's, I'm calling them join points because they behave like labels in a control flow graph. Right, so here's my little program here. Case X's, I take a case split, and then I take another case split, and then I go to J1 and J2. Why do I call it J? Because that's where you might join up or jump to, lots of J's here. So here, if you were writing it in a flow chart, you say, look at X's, look at E1, and then if E1 has one thing, I go to J2. And you can see that in terms of compilation too, you might imagine that I'm going to compile this into code that scrutinizes X, and then scrutinizes E1, and then literally jumps to the code for J1, passing X as an argument, right? When I say jump to, J1 might have some free variables. This one does not have any free variables, but it might, but they'll be on the stack. So this jump amounts to adjust the stack pointer and go to. There's no allocation for J. Mostly, let, in GHC at least, allocates a closure in the heap. Join points, these, we're going to have to be a bit more specific about what a join point is. These particular let bindings, they don't allocate anything at all. And the call to J here is literally 2 instructions. Well, sorry, put any arguments in the usual registers that you would for calling a function, adjust the stack pointer, and go to. Super efficient, no allocation. Yes? Hmm? Because it's a tail call. So these join points must be tail called. You can see the ones I've introduced had that property by construction. So yes, it's a very primitive sort of escape analysis, really, a particularly useful one. Okay? So this was the sort of key intuition. And in fact, in a completely unprincipled way, I'd had this intuition for ages. GHC, since its birth, spotted right in the back end. Did I write this out somewhere? Yes, right in the back end, GHC's code generator, if it saw the pattern of a let binding with some tail calls, it would not allocate for it. So as a sort of ad hoc, unprincipled, but useful optimization, it was called let no escape in those days. Often it had that. But in fact, then, subsequently I discovered that, all of this stuff has been known well since the very same Rabbit compiler. The same guy. This is earlier in the same thesis, and he disposes of it in 4 lines of text. Right, I'm going to devoting a whole talk, but Guy, very clever, he can do it in 4 lines. And here, look, if of if, so this is his case. If of if, he just duplicates the outer if into the inner branches. And he has the idea, of course, of avoiding code duplication using let binding. Right? Interestingly, though, this chapter of his thesis is before the CPS chapter. So he does this in direct style, interestingly. Okay. Now, so yes, so all good compilers and have been doing something like this, of course, for a long time. I don't know. I haven't managed to find out enough history about whether other compilers have done this GADT and coercion and arbitrary pattern thing. I suspect they have somewhere in reality. Not very much documented. So that was where we were, right? And then I met Zaina, right? And we got to figure out what to do, because some of this is a bit ad hoc and principled. So the idea is that we're going to stick to join points as being some kind of let binding, but a little bit special. We're going to formalize what it means. This was the process that Luke and Paul and Zeno and I then went through. Then we're going to infer from arbitrary code. Some of those let bindings are already join points, by accident. Others we might introduce as part of this case swizzling business. They're going to be join points by construction. But others we might just find. And then we're going to teach the optimizer. So when I say this leaves money on the table, if we only do this stuff in the back end, which is all I was doing, we're leaving on the table some really good optimizations that I'm about to show you that we can do if in the optimizer we know that something is a join point, right? So not just the back end, do it in the main, repeatedly transform and simplify loop, exploiting join pointness. You better make sure that the optimizer doesn't lose any join points, right? Once having discovered a join point, you don't want to lose it. Because that would make the program less efficient. And then maybe there are even some new transformations that are altogether join point specific. And I'm going to show you all of those things, because since we wrote the original paper in 2017, there's been a kind of 8-year development, and join points have slowly, like the gray goo, they've slowly infected more and more of the compiler. We find, oh, look, if it's a join point, we can do something neat here. So they're becoming more pervasive, but more pervasive in a good way. They've offered new opportunities. They haven't generally offered new problems. So that's always a nice property to have. So I'm going to try to share with you not just the idea of what a join point is, but a bit of the sort of practical experience of using them in practice and what we've had to watch out for and what has turned out to be a new opportunity. Fine. So far, so good. Any questions or observations? Yes, please.
Yes. I thought part of the point was to solve the code duplication problem. Don't you still have the code duplication problem with your original example?
Let's go back to original example. Here. Can you repeat the question? Sorry, yes, I should repeat the question. Yes, so question was like, don't we have the code duplication problem in the original program?
Well, we don't have code duplication, but we don't have the ability to, since we're not inlining here, we can't optimize away, we can't do that optimization where we flatten the two functions.
Oh, so the question is, if we do this join point splitting, I pull out the join points, do we lose optimization opportunities? Well, no, we get the one that we really wanted. The original one we wanted was, remember our original program back here. This was what we wanted, right? This case true of true, right? That was the one we were after. The outer case cancelling with the arm of the inner case, and we still get that. Look here. Here's big, big. The outer case, we don't, you know, we make into join points the arms of the outer case, this guy, but not the outer case itself. So the outer case itself, this black case, it's duplicated, case true, false, case true, false. That's still duplicated. These J bits, they're not duplicated now. So of course, it might be that if you took big 1 and made a copy here and here, that you could somehow do something that you can't if it's not put there and there. And that might be an inlining decision. Perhaps the inliner can be clever about that. But to first approximation, we're getting the main payoff by duplicating the black case, but not by duplicating its arms. Okay? That's the idea. Yeah.
Duplicating a constant amount.
We're duplicating a constant amount of stuff, yes. Yeah. Anyone else? Yeah.
Excess, the parameters can lead to the inline. I mean, the inlining chances we may be losing, isn't it?
We may lose chances to inline because?
The parameter excess, I mean, if there's a parameter x that is passed to J1, I could have used that to...
yeah, where do we, this one here.
Right.
We pass J, yeah?
Right, so if I know the value of x in the case where I'm actually invoking J1x, I could be inlining it.
Oh, well, that's true. So you're saying that in here, if in this case here, I somehow get to know what x is, right, then I might call J1 applied to 3 and J1 applied to 7 in the other branch. And so now that's like if I've got a function definition and 2 calls to the function applied to known arguments, it might be a good idea to inline the function. Well, it might, but that's the same decision that applies to all functions, not just join points. So yes, that's a hard decision, but I love the way that it's the same decision for the functions that you write and the functions that are introduced by join points. So any heuristics or magic or flow graphs or everything we do will work for both. Yeah, it doesn't make it easy. It makes it the same hard. Anyone else? Okay, let's see. Right. So here in this paper, I'm not going to take you through the paper, but I do encourage you to read it. I was a subsidiary author, so I can talk it up. So here it described a little lambda language, essentially the one I'm showing you, except that we added this join binding, join of JB. What's JB? It's a join binding, which just says it's either a non-recursive one or it's a recursive one. So it's just the same as before, like a non-recursive let or recursive let. But in this language, it has a different keyword. In the implementation in GHC, I'm going to show you, we don't use a different keyword. It's still an ordinary let. And then jump, this is a call of the join point, a jump to the join point, like one of these guys here. J1 of P, J2 of P, in the little calculus of the paper, that would be written jump J1 of P, jump J2 of P, and so that's in the term language here. Okay? Yeah?
In GHC, jump is also, in GHC.
I think you switched it on now, it's fine. No, go ahead. It's on, yeah.
Yeah. So, in the GHC, does jump represented as like a normal application or like there
yes, inside GHC, a jump to J is represented normal apply, just a call of J. I'm going to show you a little bit more about that in a second. So I'm going to show you in a second how we map this onto GHC, but this was the language of the paper. So the language of the paper, having got this, we could then say, oh, and then here are some typing rules for the language of the paper. And you notice, I'll mention this later, but briefly, but J, these join point guys have a slightly funny types. They have type for all A something, a bunch of sigmas, arrow for all RR. That's a funny thing. So that looks a bit suspicious. It looks as if these join bindings bind variables that have weird types. So we're going to come back to that. And then there's an operational semantics that justifies the stuff I said about we don't do any allocation, and when we jump to a join point, we adjust the stack and jump. So look at this rule here. This is the operational semantics for a jump, and it says if on the stack I've got arbitrary stuff followed with a join that binds that j variable, then I just throw s prime away. I abort that chunk of the stack, adjust the stack pointer, and resume execution with the remainder of the stack, that's little s guy, right? Keeping the join bindings, though, because they might be recursive. Okay, so again, I'm not going to go through all these rules. I just want to encourage you to believe that, with Zeno and Paul and Luke's guidance, we've got an operational model as well. Okay, all right, so how do we map all this, which is really what this talk's supposed to be about, onto a real compiler? Well, it goes like this. A join point binding we're going to map not as a new kind of construct, a new data constructor in that core expression type, but rather just as an ordinary letrec binding. So in fact, inside GHC, the way it's tagged is the binder itself has a little tag on it to say, I'm a join ID. Right? You could imagine join IDs being drawn from a different alphabet, if you like. So in a let binding, these J's are drawn from a different alphabet. So I might write join J, but all that means is that's let J, in which J comes from the join point alphabet, okay? And also, sometimes I usually write the binder on the left like this, but it's just ordinary lambda. So J equals lambda X. It's just the same lambda. It's not a special sort of construct at all. I should really have put, in this mapping thing, it would really be able to say J equals lambda X, dot right-hand side. Okay, anything else to say here? No? Okay. So, so that means that I said almost exactly like. What is exactly the same and what is different? It has the same representation, modulo this little tag on the binder of these binds to say I'm a join ID. It has the same semantics. This is very important, that if you take a core program and forget about the join point binders altogether, just turn them all back into ordinary let binders, everything runs the same. That's a good property, right? Because it means that you know what a program means. But it has slightly different operational behavior because a call, an apply of a join point binder is one is adjust the stack pointer. And also for lets, instead of allocating a closure, we don't allocate the closure, we just remember where on the stack to jump to, okay? So it is almost the same. The point that I think, yes, that's right, and making it the same, as let bindings, is a really big win. Right, why? Because, well, no need to add extra cases, that's one thing, right? So if you've got lots of GHC passes run over, deal with let expressions, mostly they can, to a first approximation, they can deal with join bindings the same as let bindings, like finding free variables, the same, right? Zero extra code, that's good. Inlining behavior, we were talking about that, right? With our colleague here, right? So inlining behavior, exactly the same rules apply for join points. Sometimes you think, maybe I could tweak it a bit. So there's room for tweaking, but to a first approximation, it's the same. Strictness analysis. Wow, this is a big deal in GHC, right? Or we're trying to figure out which functions are strict. If a join point is strict in an argument, we can do the same worker wrapper nonsense and so forth for join points as we do for ordinary bindings. That's really good, right? So not a whole new kind of thing. And also, as we'll see, there are some new opportunities we get. To first approximation, we can just use the old thing. But I do want to draw your attention to the fact that it's not quite what the paper says. So this, I don't think, is documented anywhere except in GHC's source code. So you heard it here for the first time. The thing that GHC implements is not quite what is in the paper. So look at this. Join JX. In the paper, you can write this. Join JX equals blah in case jump J3. In the paper, this is fine. What does this mean? This says, well, look, when I start to evaluate this case, as it were, operationally, you might imagine, I push a return address on the stack, and then I come to jump J3. What does that mean? Adjust the stack pointer and jump. So I'll throw that return address away. I'll abort that continuation. So as far as Zeno is concerned, Simon, what's the problem? right? It's just the obvious thing. But this is not what ordinary let bindings do, right? If this was an ordinary let jx equals case j3, right, we'd literally call that function and return to the case, this abortion thing. In other words, the forget all about join points and it should mean the same thing would no longer hold. It was discomforting. It's, you know, the join point bindings is no longer just an optimization, it's actually crucial. And moreover, I showed you briefly the funny type that join points have. That's a little awkward as well, and it's very convenient not to have funny types. If they're the same as let-rect bindings, no funny types, that was good. And moreover, this thing is completely useless, right? What's the first thing we're going to do? Oh, we look at this and we say, case J3, we're going to always throw that case expression away, right? Just turn it into this. Throw it away statically at compile time. So we just arrange never to generate these kind of programs, just always to generate this one. So the extra generality had costs and it had no benefits. So in the implementation, it's a little bit less general than what's in the paper. But I found that was a compromise that worked really well. Yeah?
So does that mean that if the simplifier has something that transforms a program that already has join points into a form where the join point call is not in a tail position, then things are going to just go wrong?
So if the question is, if the simplifier sees you know, a program in which the join point is not in a tail position, do things go wrong? Well, it's going to start with a program in which join points are always in a tail position, because that's the invariant, right? Now, what the simplifier arranges never to construct a program like this one. Yeah?
But if it did, then you would get
Oh, if it did, then, oh, so you might say, what if we made a mistake?
Yes, exactly.
Yeah, what if we made a mistake in some pass, and we took something that began life as a join point, and we turned it into something like this? That would be bad. But fortunately, where are we? Yes, fortunately, we can catch it rather easily. So the way that GHC's optimizer works is we run this little sequence of 3 passes a lot. And it works like this. Occurrence analysis is a bottom-up pass that finds how often each free variable occurs in the expression. Right? So the result of occurrence analysis is a little finite map from free variables to number of occurrences. Actually, it knows a bit about whether there's multiple occurrences in different branches of a case, but to a first approximation, how many occurrences? When we come to a binder, we say, oh, now I can see all the occurrences of that binder. It occurs 3 times. I'll tag that binder with the number of its occurrences. Maybe 0 times, maybe 1. That's helpful because then we can definitely inline it, maybe many. Right? So occurrence analyzer, bottom-up pass that decorates the tree with occurrence information. Then the simplifier does a lot of things. It does inlining, it does case of known constructor, it does constant folding, it does rule rewriting. It's a big smorgasbord of individual optimizations which are all smashed together into one pass. And then, and this is what I was to respond to your question, then optionally you can run lint. Lint is a type checker for core. Right? So it checks that everything's type correct. It's system F, so it's fully type checkable. And in particular, it checks that everything that claims to be a join point is actually, in real life, a join point. So if you screw up and you, generate this, the next call of lint will blow up. Right? So if your Haskell program ever falls over with a mysterious compiler-ish error, always switch on lint. Lint is not on by default in production because, after all, if the compiler's correct, lint will always say yes. But if anything's gone wrong, you switch it on as your first debugging mechanism. Okay, yeah.
Hello. So in the paper, you have an equational theory for join points.
Yes.
That really uses this explicit jump and, for example, also has an equation for throwing the continuation away.
Yes.
Do you still have a nice equational theory
without
the explicit jumps?
Yes, I'm going to show you. Okay. Yeah. So this is, in fact, this is a nice segue into what we're going to do next. Yes.
Are those join points just fancy tail calls?
Are the join points just fancy tail calls? Yes, I suppose. Yeah. It's just an ordinary let-rect binding with a particular property that, oh dear, I've forgotten. I've got a slide that lists the properties. Oh, here we are. It's the particular property that a join point has. If I've got a let, I might say of an existing let, is this let a join point? Well, I could say, oh, look,
All of its occurrences are tail calls. None are captured in closures. They are all saturated. Yes, it's a join point. So the occurrence analyzer, as part of its work in doing this bottom-up pass, as well as now capturing how many times things occur, it also captures which things are tail called with how many arguments, so that it can tag all the binders with, is it a join point?
Yeah, see, so the tail call plus 2 more properties.
But, yeah, that's right, plus some more. It has to be, you have to be careful about the return type cannot mention any of the type parameters of that same function. So there's just a couple more properties, but yes. And so accidentally or coincidentally occurring join points are identified as such in each one of the occurrence analyzers, and thereafter we'll tell you if you ever screw up and lose it. So it's like a ratchet. You know, you get more and more join points and you never go backwards, right? If you ever lose one, then you get, Lynch will complain. Yeah.
Having join points as tail calls clearly is an efficient way, but if it is not a tail call, can it not still work? Because the way you explain it seems to work either way.
Can a join point work if it's not a tail call? Here is something that is not a tail call. So in the paper, this does work, but in GHC, as I've explained, it does not. So in GHC, I've chosen a slightly less general form of what could be done, because it's a better fit with, I'm pretty confident it's a much better fit with everything else that's going on. That's what compiler design is all about, collections of compromises. This particular compromise, I think, is a really good one, because I think it has no costs and a lot of benefits. I like those kind of compromises. Anyone else? Okay, so, someone over here, sorry, yeah.
So actually, what's the advantage of the approach done in paper?
What is the advantage of the approach done in the paper?
Yeah.
Well, it's a bit more general, but as I say, I don't think it really has any advantages. Luke, do you agree? Yeah. Okay, so, I mean, as it were, the approach in the paper is a sort of what you get if you come at it from the, what's the sort of principle, you know, the sequent calculus hits the direct style join calculus, what's the most general outcome, and that was, that was the sort of synthesis, right? And then we just made it a bit more practical and found a way to do so without really losing anything important.
So it's, in a sense, it's just the most general or like a most natural way to come up with the calculus.
I think it's more natural to somebody like Zena, yes. But it wasn't more natural to somebody like me. I look at it and say, that's not a join point. Zena says, of course it is, Simon. No. Okay, so now let's talk about optimizing. So now, we talked about inferring join points. The occurrence analyzer infers the occurrence of join points. Yes, oh, sorry, go.
So there's two sources of join points, right? Some that start life as a join point because they're introduced by case of case.
Yes.
Some start life as a normal binder and then inferred to be a join point.
Yes.
My question is, are recursive join points only ever coming from inferred join points, or is there situations where you would create a...
I'm going to talk about recursive join points. And indeed, they are never constructed by this case-of-case thing. They only show up through inference. Okay. Yes. This what's called quantification in other papers. If you see quantification, sounds scary, but this is all it means. Actually, it looks a lot more complicated when you do it in CPS. Here, it looks rather simple. Sorry, I couldn't resist a little dig. Okay. Now, so now, let's talk about the opportunities you get when you optimize a program that when you know that there are some join points in it already. Here is a transformation that is really good in general. Case of let x equal blah, 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 just ordinary let expression. It's a really good idea to float the let out. Why? Why is that? Why is it a good idea to pull the let outside here? Because? What was that? Common sub-expression? Yes, but there's something even closer to home. What might body be? Yeah. True, it might be a constructor, yeah. If body is a constructor, then I can do case true of, but if there's a let in the way, that's less obvious. So putting the let out of the way is very helpful. So, forever, GHC has floated lets out. That's clearly a good thing to do. But it's not such a good thing to do for joins. And it's bad so this is a slide which gives you, I think, some new information that took me some while to absorb. So if there's a join point here, look, this join point is only called once, but never mind. The red guy is a little expression with a join point in it. If I float the join point out and then do the case-of-case transformation, I get this thing, right? Because now the branch of this is a JX. The black case goes in and scrutinizes the JX, case JX of true-false, and then case E2 of true-false, right? That's what would happen. Two bad things. Number one bad thing, J is no longer a join point. Look, it's not tail-called anymore. Parche Zena. But even worse, the outer black, this black case here, is now scrutinizing JX. It's not scrutinizing E1. If you imagine inlining JX, so in that case it'd be just X arrow E1, well then the black case would scrutinize E1. We love cases that scrutinize E's rather than calls, because after all E1 might be true. Yes, might be true. So by abstracting out the J, that would be terrible, wouldn't it? So two very bad things. We've lost a join point, and we've lost an and the join point has made things worse. Is that what the next slide says? Yes, the join point has made things worse. If I didn't have the join point, if I just had E1 there, I'd get better code. Abstracting it out, doing this business of sharing, it's back to what somebody at the back was saying. I've lost an opportunity by having abstracted. It was, yes, it was you at the back, Lyle, wasn't it? Yeah. By lifting out the join point, I've lost an opportunity to cancel this black case with E1. But what's the obvious thing to do? It's to exploit the, well, what we want to do then is to, well, look, we'd like to move this outer black case. Its business is to scrutinize E1. Look very carefully. Look, this outer black case, we'd like to duplicate it into the arms of the J, so case E1 here. And then in the red case here, this guy, instead of the J, I'd like to just call J prime and not have the black case. So the black case, the crocodile, has instead of the crocodile, instead of eating JX, has eaten JX's right-hand side. What a simple idea. Do you get it? Yeah, Jeremy.
It's puzzling me. You've been saying that the join point is a tail calls, but up in the top example, J is not.
Sure it is. It's a tail call. Look, the binding here, if I'm evaluating this expression, then all I do is I have J, so I've got something, I've got my stack frames and everything. Then when I come to call J of X, I just adjust the stack pointer and jump. It's a tail call. It's a local tail call. I mean, of course, tail calls are always relative to some scope. Yeah. So at least for, never mind, we'll just define it. This is the definition, right? And you may not call it tail call. Let's call it wombat call. But wombat calls can be done efficiently, whether or not they're tail calls. Yeah.
Would it be correct to think about join points as if I install a reset around the join point and I replace an application with a shift into applications?
Now we're getting into I don't know. So I once wrote a paper with Amar Sabri on delimited continuations, and at that point I'd sort of hash included just enough to think about chunks of stack, but I can never retain it enough. So I don't think I can give a meaningful answer, but maybe somebody else can. Jeremy, can you do? Maybe, okay. Anybody else? Okay, you're not going to give a meaningful answer. Anybody else want to give a meaningful answer to that question? But it's something to do with it kind of dilemma, because there's something about, aborting a chunk of stack, which is very much like what happens with shift and delimited continuations, at least. Yes?
I think if you install a reset and you change the application to a shift, it doesn't change the semantics. I think that's what a join point is.
Okay.
Was the question on one-shot? One-shot delimited continuation?
Oh, yes, these guys are one-shot. They can be recursive, though, in which case they can call themselves. We'll see in a sec. Yep. Okay? All right. So this part is important because this is, the big insight that I finally learned, that this is how we can exploit join points. If we know that it's a join point, we can do much better when we're optimizing code. Right, we're going to do this. We're going to push the continuation into the right-hand side of the join point. And this is the rule, coming back to the equational theory question. This is the rule from the paper. It says, here's an evaluation context. If an evaluation context scrutinizes a let, an ordinary let, then we just push the evaluation context into the body, right? But if an evaluation context scrutinizes a join, we duplicate the evaluation context into the right-hand side of the join and into the body. Don't you think that's beautiful?
Oh, but you just duplicated.
Oh, we've duplicated E, yes. But we know how to avoid duplicating E, right? What are we duplicating? The black crocodile. If R1 and R2, I mean, look, like here, this is what I said we should do. Of course, if R1 and R2 are big, we would just let bind them to be join points. It's turtles all the way down, right? Okay, so we can avoid duplication. Yes? Thank you.
Really like look and see if there's a big thing and then join point it if so?
I'll show you a bit of code from GHC in a sec, and please ask your question again when you see some blue typewriter font. Okay. All right. So we're literally going to implement this this game about duplicating this continuation, and then the and this shows up directly in this code. I'm not showing you how I've done it, but the result of doing it is we've duplicated E. This E thing is the black guy, and he gets he reappears here once in the right-hand side of the join point and once in the F, right? So it's a very direct story. Now, and for jumps, what happens? E of jump is abort E, throw E away. Isn't that lovely? It's lovely throwing things away. And where did that happen? When we had this J here, we pushed the black crocodile around the J, and because he's a jump, he threw away the thing and just turned into a call to J, admittedly with a different type, as we'll see shortly. Okay? So it's very, very direct. Now, here to answer your question is, so GHC simplifier is a pretty direct implementation of this evaluation context style evaluator. The simplifier takes an environment, an expression, and a continuation of some kind, and produces a new, it's in a monad, it produces some new expression. Now, so what's this continuation? Well, the continuation is, it's just a zipper. As we walk down the expression, we just stack things into the continuation. It's exactly a zipper for expressions. So cont is stop, or apply to, or select, and then there's a few more. And so here's the case for apply. Well, when I walk inside an apply, I'm going to simply evaluate, that should say fun, in a continuation in which I pushed arg onto the stack, right? The continuation stack, right? I've just walked down the zipper one stage. And for case, I'm going to push that onto the stack, right? Select is like a case with a hole in it. So this cont guy is precisely E. He's the evaluation context. And then, let's see. This is not, I've oversimplified this because it is in a monad, and this wouldn't, I've written it as if it wasn't monadic. But for a, if I've got a join point, if this is a join point ID, I push I simplify the right-hand side in cont, and the body in cont. That's precisely doing this E duplication here and here, right? And now, to answer your question, in the real code, of course, we've got to take cont and say, make it duplicatable, right? There's a call first that said, give me cont prime, which is a duplicable version of cont, plus possibly some bindings that must be wrapped around the result. So it's a simple and generic thing that happens in quite a few places. One-off thing, take a cont to a duplicable cont plus some bindings. Yeah. Okay? All right.
Gist of that, you just go down one level in the AST and join point everything?
We go down one. Oh, yes. So you mean when we're making it duplicable? Well, remember, to make it duplicable, like we could take just one example. Maybe here's an apply to. If this is a big expression, then I don't want to duplicate that. So I'll let bind the big expression and make a small apply to that says apply to a variable, say, right? That's a simple thing to do. You can do the same for these guys. And once you've done that, then if you make that duplicable again, well, they're already small, so we don't need to duplicate anymore. Yeah. Yeah. Over here.
If cont is E, then what is N?
Say that again?
If cont represents E, then what is N?
What is N?
What does env do? Like the first argument to simple.
Oh, env. Oh, this gives you, there's lots of stuff going on in env. It's like, because remember, we're also freshening variables, and if you've got a let bound variable, you need to know what it's bound to. So you can there's lots of stuff in env. There's the mode flags of how much you're simplifying, lots of stuff. It's a big ball of wax. So, but have a look. This is fairly faithful to what GHC simplifier really does. And I really like the fact it really does use evaluation context very directly as a data type. Okay. just a quick remark is that when we push something into the right-hand side, of course, that may make the type of J change. Right, look, here's a join point J, and I'm going to push this continuation in. Well, this guy returns a char, but by the time I push the continuation into it, it's now returning a string. So it's not the same join point anymore. It's a guy with a different type. You just need to be careful to keep the types right. Okay. And that's also why we get a restriction on join point. Join points cannot have as their return type something that is locally bound in a for all here, because after all, here you might call it with int in both times. But if I push something into the right-hand side here, it would really be expecting to consume an int, because that's what both of these guys return. They both return an int. The continuation here is expecting an int, but it would find a right-hand side of type A. Not very good. So join points are not allowed to have this kind of type. That's a little type restriction on join points. Easy to enforce. But I'm not going to linger here. But this is the sort of reflection of when I say join points have funny types. They have perfectly ordinary types, but slightly restricted. Not any old value can be a join point. Okay. Right. Now, how long have we got? We got a total of 20 minutes from now. Is that right? Beg your pardon?
20, yeah.
20, okay. So we have to speed up. Recursive join points. So I was delighted when I discovered that recursive join points just work. As Gergo said, this is only done by, they only occur when you infer them. So here's last, a recursive function that finds the last element of a list. Well, so its calls, possibly in its own body, are tail calls. And so we make it a join rec. Well, actually, it's just a let rec, in which last is marked as a join point. And then everything just works out. It's not allocated. You can jump to it, and its recursive calls, it just jumps to itself. It's a nice type loop. It's very much like what people sometimes call loopification. Everything's very simple. The occurrence analyzer discovering this, very straightforward. So it's another of those things, amazingly, that just worked out very nicely. And we discovered, unexpectedly, that we got some new fusion opportunities we never had before. So so here is a stream data type there's a whole little research cottage industry on streams. And just this look at this little guy here. So this has a lambda s and then a let rec here with a recursive function that really is a join point here. That's good. And now filter, supposing you compose this filter s function with itself. So you'd like a filter stream function to somehow, you don't want it to produce an intermediate stream. You'd like those to fuse away. And while this is a let rec, it won't fuse away. But when it's a join rec, it turns out it does fuse away. And the details are in the paper. I'm not going to spend long on it. But the key step is that we end up with a case that's scrutinizing a join rec that looks like this, right? There's that step function in here. He turns into a join rec, and we end up, as you will be able to work out if you do the the book work, we end up scrutinizing a join rec. Now, when we scrutinize a join rec, what happens? Well, we're just going to push this case into the right-hand side, and so this case blah ends up wrapping around this right-hand side, this right-hand side, and this right-hand side. So we get case done, case yield, and then a tail recursive call to step again, having aborted the continuation, right? And look, now we've got a case of a known constructor, because blah is probably scrutinizing done and yield and so forth. So in effect, the continuation, which is scrutinizing the result of this is like that last function. It runs around a loop and finally returns something, and the continuation, the case blah, has zoomed in to the return branch when we finally exit. That's very nice. So in fact, we get beautiful fusion without any work at all. That's rather satisfactory. Okay. So much for those. Now, just a few other things that I found in experience reports from optimizing with join points. Here's an example with a let rec and a call to f that is not a tail call. So it's not a join point at all. But GHC, among other things, floats lets inwards to be near their occurrence site. If you do that to this guy, look, we'll float that letrec, we'll go 1 plus letrec fx equal blah, 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 in fy. Now it's a join point. So moving functions, this doesn't always work, but floating lets inwards makes new opportunities for discovering join points. That was a nice discovery. It's not magic, but it's a good thing to happen. Inlining, super important. As I've remarked already, the inlining transformation already tries to say inline small things, even if they occur many times, inline big things if they occur just once, so that happens automatically. And then what else might we do? We might need to be careful of, this is something we might need to teach the inliner that's new. Usually we're careful about inlining inside a lambda, right? This V, here's a thunk f of 22. Usually if we've got a lambda, we'd be careful about inlining into its body because the lambda might be called many times. But non-recursive join points are called once. They are one-shot lambdas, one-shot continuations, right? So this lambda is sort of special. We can definitely inline V into it. So teaching the inliner that join points can only be called once just by the virtue of being join points is easy and very effective. Another, even a trickier example that showed up, this I only did about 2 or 3 years ago, so relatively late in the game, is this. Suppose I've got this, not join point, just an ordinary let binding. There's a small expression here, and I scrutinize it several times. If I inline it, then several things might happen. The first thing, I might get case of known constructor and all of that. And also, here I'm going to allocate a closure for small. Here I won't allocate a closure for small, I'll just call it. Right? If small was, factorial x, here I'd allocate a closure, a lazy thunk for factorial x. Here I'll call factorial x. So less allocation, and also no allocation at all in this cold path, well, this path that doesn't, maybe this is the hot path, in which case I don't want to allocate small. So this kind of inlining can be quite effective in improving performance. But look at what happens if I made it into if it was a join point instead. So now what happens? I've got this V guy, but now V is really only evaluated once in the end. Look, on the A branch I call J, that evaluates V. On the B branch I call J, that evaluates V. On the C branch, V is evaluated here. On the D branch is not at all. So it would be safe to inline it at all 3 occurrences, just like before, right? But it's not so obvious because V is now occurring twice, right? Occurring twice. And it's no good saying, well, one is in a join point and one is not in a join point. If it was, it might be looked at on the way to the call of the join point. So we have to be careful here. So this was a place where for some while, GHC was behaving worse with join points because with this version, it would inline like crazy and good things would happen. And here it wouldn't inline and less good things would happen. Join points were making things worse. But what we have to do is just to be a bit cleverer in the occurrence analyzer and behave when J occurs as if you had inlined it. So the occurrence analyzer tries to behave just as if non-recursive join points were fully inlined. It doesn't actually do that, it just behaves as if and does occurrence analysis on that basis. That's enough. So that wasn't obvious to me. It might not have been obvious to you, but I'm now your experts. I hope it will be. There's a little wrinkle that was quite cheap to implement, well worth it. One other tricky corner. I'm still trying to show you tricky corners. This had me baffled for some time. Look, if I have this guy, this is the outer case. Oh, the outer case was usually black, but the crocodile has turned red. If the red crocodile eats this guy, I'm going to get case KFX. That's good. All right. Very good stuff, but this F guy is simply a free variable, right? He's defined in the enclosing scope. Perhaps he's bound to a lambda, a known lambda. So here, I end up with a call to a known lambda. Everything is good, right? I'm happy. But what if instead let's see, if I inline this join point, look, it's small. Surely I should inline this small thing. Let me inline it, it's 3 sites. So I get KF1, KF2, KF3. Now what happens? Oh, very bad. Now, look carefully. The red crocodile scrutinizes, the right-hand sides, and, I beg your pardon. This might be big, so we're going to make a join point for him, here called J1, J1GY. And then, in the A case, we'll end up scrutinizing so that the case cancellation will still take place. We'll still KF1 of KGY arrow, we'll call J1, and the same here and the same here. All right? And so we'll end up with this code. We'll call J1 of F, J1 of F, J1 of F3. Oh dear, this is very bad. See why? Why is it bad? It's a indirect call, that's right. Here, I'm calling this G function, which is passed to J1. I'll give the right answer, of course, but here, I knew that F was this lambda. I could inline it and optimize more inlining could take place. Here, as it happens, G is always F. Well, some flow analysis might work that out, but I'd rather not make that mistake in the first place. So this is a little ad hoc-y. At the moment, we're just careful about if a join point right-hand side looks like a data constructor, I'm careful not to inline it. On the grounds the continuation will then see that data constructor. So I'm not very happy about this because it seems a bit more ad hoc and unprincipled. But inlining is an ad hoc and unprincipled transformation, really. GHC has a collection of not very satisfactory heuristics. A very few people, like Lionel and Celeste, have worked on improving GHC's inlining in general. I would love more research. Any research students here? I would love you to work on making inlining more principled. And work better, too ad hoc. Okay, 10 minutes ago? 5. 5, okay, so then I'm going to skip exitification or exit floating. This is a transformation which you can, I'll leave the slides on my homepage somewhere. That is a transformation that identifies exit points of loops and pulls them out of join point right-hand sides. But I think I'm just going to skip this in the interest of time because I want to finish in a polite way, and here we are. In fact, this is the last slide. That's good. I like the fact that this is almost embarrassingly simple. I hope that everything I've shown you, you think, well, of course, all right? Nothing hard here. That is the key to building compilers, is to find simple things. And so I think if you're building a direct style compiler, well, if you're building a CPS compiler, you might think of doing it in direct style after all. If you're building a direct style compiler, it's really worth paying attention to first-class join points because they're very simple to implement and they give really a lot of payload. And while you might want to make some more comments and ask some more questions, I'm going to leave you with a question is, tell me guys, the things you can do in your CPS-based compilers that you can't somehow do using this, because I'm still on the lookout for those cases so that we can, I can understand better. Any other questions or observations from your own experience? Observations are absolutely fine, by the way, from your own experience. Yes, Robert.
If you go back to where we were talking about like the fusion for the stream filtering.
Yes, yes.
And we were like pulling the outer case into the branches, and in one of the branches we got rid of it because we were calling a join point. Isn't that I think
here.
earlier than this?
Yeah.
I think the slide after this.
Yeah,
here. So here in the jump step prime case, we get rid of the case that we floated in. Isn't that doing the thing that we said the paper did, and we don't do in the implementation? Where
No, that getting rid of the continuation around the jump is precisely the. Now we have to go back quite a ways. It's precisely right, this guy here. So the evaluation context, when it hits a jump, we throw away E and just leave the jump, right? And we really do implement that. That is not the bit that GHC does not do. GHC absolutely does this. And that shows up in the simplifier that when it comes across a call to a join point, right, it discards cont. Exactly as it looks like here, right? Except, I mean, it's not quite the same join point because it may have a different type, but you still get a jump with the same arguments. So
Wait, so where's the distinction between that and the thing that we don't do? Is it just that we don't allow it to be like explicitly written like that?
No, the distinction that we don't do is that in situations like, yes, here, this one, as far as GHC is concerned, this is not a join point at all.
Ah, okay.
Right, just isn't. Right, GHC's definition, no, not a join point. We never have to think of, so it's not marked as a join point. It doesn't enjoy any of these special properties. Right? We just arrange that if you give me this program with a let, I won't infer it as being a join point at all. No, and indeed it isn't. But if you give me a program that does have join points, I won't ever construct this as a result of a transformation. So it's,
right. Okay, thanks.
Yes,
Mike.
Are we done?
Yeah, we'll have a 5-minute layover, but it would be nice to unplug the computer. Trace can set up.
I can unplug
as
the
a question. We'll have 5 minutes. We can take a few more questions.
It seems that laziness saved you a few times in...
yes, hi.
Laziness saved you a few times where you could do some transformations based on the fact that you're in a lazy language.
I don't, can you give me an example? Because I don't think any of this depends on laziness.
I think there was one case where you lifted out a let somehow.
So I did say that when we create a join point, I could give it no arguments at all because I'm in a lazy language. But actually, when it's a join point, even in a strict language, it wouldn't be something you'd evaluate call by value. A join point in a strict language, you just say, I'm not going to compile any code for that. I'm just going to adjust the stack and jump. So I think it's fine in a strict language as well. I think this is, my hypothesis is, everything I've said will work hunky-dory in a strict language.
All right.
I hope. If you find a counterexample, it'd be interesting to talk about it.
Yeah, one more. Hang on.
Yeah.
2003, I first heard you giving a keynote speech. 22 years down the line, you have gone 22 years younger. Thank you. I had one thing about the CPS where it's used. So we compile OpenMP programs, and we find that with CPS, with
guys, can you be a bit quiet? As I can hardly hear the question.
With one-shot continuations,
yes,
with CPS, right?
Yeah.
We are able to obtain wait and resume. That is very difficult to do with natural style compilation. So with CPS, we are able to do wait and resume, which is amazing.
Wait and resume.
So we are mixing the two.
In a concurrent program?
In a concurrent program, yes.
Oh, a concurrent program.
Yes.
Right.
That's a place where we are mixing both. And we are getting good.
Once you get concurrency, then continuations, of course, rear their heads in a different guise. Yeah.
Just a bit to your question.
Yeah.
Thank you.
Okay. Concurrency. Yeah.
Very short.
I just feel like, I'm not sure if you're aware of continuation-based partial evaluation by Olivier Donvy and Julia Lewald, but I think they do something very similar. So basically, before that paper, people didn't know how to ether expand case statements. And ether expansion is really important for partial evaluation because you can shift cases in and out, depending to match it up. And I suspect that this is very similar to what join points are doing in a way that I can't quite express. Right
okay,
now.
well maybe you can figure that out because, of course, I'm not saying continuations are necessary. Continuations are a whole field of wonderfulness, right? I'm just being sort of teasing you slightly about, don't use CPS. There's lots to be had. So, but if you make that connection clearer, that would be great. Good.
You should take the mic off.
Oh, microphone, yes. Would you like the radio?
Simon. Oh, yeah. We have 2-ish minutes. Right. We're starting in a minute. Okay. Welcome to our second talk. Everybody seated? Yeah? So please welcome Travis Caldwell, who's going to talk to us about C bindings. Take it away.
Thank you very much. Today I'm talking about automatic C binding generation for Haskell. This is a project that I'm working on with my colleagues at WellTyped. And I'll introduce the project soon, but first I'd like to sort of explain why foreign function interface is important for Haskell. I think we'd much rather use Haskell. We have type safety and types. But foreign function interface is very useful in Haskell for a number of cases. One of them is to interact with other software. So on your system, if you're running your window manager or something, you need to use foreign function interface to interact with that software. You may want to use foreign function interface to use audited or trusted implementations. For example, cryptography software is notoriously hard to implement, so using an audited library is usually a good idea. And it's also useful for interfacing with existing implementations. Maybe FFmpeg is not what your core logic is, so you can just use FFmpeg to implement these video transformations and work on your core logic in Haskell. And then perhaps later, if you have time, re-implement FFmpeg in Haskell if you want. So creating and maintaining FFmpeg bindings can be pretty tedious. Haskell and C are quite different. With C, you have to worry about memory management. The C types are quite different. And when you're implementing the Haskell, there's a lot of boilerplate to implement these kind of bindings. So we're trying to improve on that situation. So today I'd like to introduce HS BindGen. HS BindGen provides fully automatic generation of Haskell FFmpeg bindings from C header files. And the design of this library is, or the design of the utility is based on these core design principles. The first is automation. We aim to produce bindings without user input. You can always use overrides to configure how bindings are generated, but that's not required. Our goal is that for most cases with sane C projects, you can just run this and get Haskell bindings that you can already use. We also strive to preserve semantics, both in explicit and implicit semantics in the C code. I think Haskell distinction of types and being able to provide instances for new types, for example, is very powerful. So in C, you usually have typedef type aliases that are the same thing, but we want to be able to preserve those semantics where needed. And we also want to provide predictability so that code generated by HS BindGen is clearly predictable from the C code, and that's just to make the tool much easier to use. Given some Haskell code, it's easy to understand where that's coming from. So I have one motivating example here that's quite simple. This is a .h header file that defines just a data type, struct point, and a function, print point, that perhaps prints the point to the screen. So these are just very small 2 declarations in C. What do you have to do to create Haskell bindings for this? So first, you have to have a data type that corresponds to struct point. You have to implement a storable instance for that type so that you can marshal the memory from between the Haskell and the C world. You have to write a C wrapper function that is compatible with the Haskell FFI. So here you'll notice that the print point passes a struct point by value, and Haskell CFFI requires passing arguments by reference. So Haskell CFFI cannot use this function directly. So generally you have to write your own wrapper function to work around that limitation. And then you need to write a Haskell function that corresponds to this print point, that allocates the memory and calls your wrapper function. So here's how I would write manual bindings for this case. So this is the header file that defines this wrapper function. So since this is a static inline, both the declaration and implementation can be implemented in the same header file. Here we have a function wrap print point that takes the argument as a reference, and then it dereferences that argument to call the actual print point function. Then implementing the Haskell code, this example uses the HSC to HS library, which I'll explain on the next slide. But you can see that it defines a data point type that very closely corresponds to the C struct point. It's pretty straightforward to just translate the code over. writing it by hand for all the types can be pretty tedious. Then you need to implement a storable instance. Here is where the HSC to HS tool comes in handy. The storable instance has to have the size, alignment, and the offset of fields for your type defined, and that is all platform specific. So when you're using HSC to HS, it runs C code at build time that finds the correct constants to insert into these hash locations and creates the correct Haskell bindings for your current platform. So then we also have a foreign import call down here, and this is a call that imports the wrapped print point function. So you'll notice on the previous slide that we have a hash include point wrappers.h, and this is importing from hash include point wrappers.h wrap print point for the pointer API. And then finally, we can write our print point, which uses the foreign with function to allocate memory and call our print point wrapped function with that pointer. So even though that we only have 2 declarations in C, this is a lot of code coming out. And you can see why I chose a small example. HSBindgen can generate all of this code for you. So I'm skipping the common imports, but here HSBindgen generates this data point, which is very close to what I would write by hand. You'll notice that the names are all generated automatically, so the users do not have to specify the names. And then the storable instance is also very similar. You can see that it's generated code, so we're using lambdas and de Bruijn indices. But the constants are all coming, all defined in the generated code. This previous slide is an example of the types that are generated, and then we also generate submodules for functions. So we have unsafe, safe, and function pointer submodules that allow the user to decide what is the appropriate way to call your C functions. And here we have a C API add C source template Haskell function at the very top. This embeds this generated C code that's shown below. So this is also very close to what we write in manually. It's just a function that takes a reference to a struct point and dereferences it to call the actual print point function. There's a lot of, I thought I knew C very well before starting this project, and I've learned that there's a lot more that I didn't know. And there's a lot of devil in the details. And so you'll notice things like these hashes. There's like limitations on the C length of identifiers and things. And C headers are all in one single namespace. So there's all kinds of details that require these kinds of tricky implementations. Okay, so all of this code is generated by HSBindgen. You don't have to write any of this, and you can just use the library. So as a brief overview of the architecture, HSBindgen is designed sort of similar to a compiler. We have a front-end pass that incrementally processes and annotates a C AST across multiple passes. This is using the trees that grow style annotations. And then we have a backend that has It takes the final AST from the front end and then translates that to a Haskell AST, transforms that to a simplified version, and then goes through the preprocessor or template Haskell backends for code generation. So today I plan on going through a few common questions that will sort of illustrate the design of this project, and then go through one case study. So first, the big question is, how are the C headers parsed? We use libclang, which is part of the LLVM project, to parse the C headers. So this library parses the C headers and exposes a libclang AST. So then we can traverse that AST and create our own internal HSBindgen C AST. One interesting thing to note is that this is the only pass that is using I/O. All the other passes are pure. So we have to use libclang to create the initial AST, and then we have pure passes that can iteratively refine that AST and generate code. And it's libclang that determines the sizes and alignment of types and the offsets of fields So LLVM is a targetable compiler. You can pass the target architecture. And so HSBindGen allows you also to specify a target, and you can generate bindings with the correct size, alignment, and offsets for different architectures. The naming is a very critical part because it has it's one of the very user-facing sides of the project. So to name, we construct what we call a use-def graph. And this example is a bit convoluted. It contains many anonymous structures. In C, you don't have to name structs. But the reason why I chose this example is to show how the names are nested. So this example has an anonymous struct that's defined on line 1 that's used by reference in the typedef top level. So we have a graph that shows that this :1 is our initial representation for anonymous structures. It's just like the source location is used by typedef, used by ref in a typedef. And then inside that, we have 2 anonymous structs that are used in fields of that outer anonymous struct, and they're used by value, inner1, inner2. Then there's one more internal anonymous struct. Given this use declaration graph, we can assign names to the anonymous declarations. We use the @ mark to denote anonymous. So this anonymous struct on line 1 is denoted as struct anonymous top level underbar deref. And you can see here how as you go into the nested declarations, you just sort of add underscores and suffixes to show exactly what the name is. So one slight detail is that in C, each struct has its own namespace. So you can't just have simple C name to Haskell name because you'll have collisions all the time. That's why you have to go through such hoops to name anonymous things. And these default naming rules are not customizable. This is to support predictability. You use these names when interfacing with the system, and being able to easily guess how the name should be makes it easy to use. And then, of course, these names have to be mangled to create Haskell names. That's relatively straightforward. There's differences between Unicode, like valid names in C and Haskell, so there's lots of details. But in general, you just take the C name and so the names of types and constructors have to have a first letter that's uppercase, while other names have lowercase first letter. Excuse me. But there's many cases where you want to customize generation. So we have a data type called a binding specification that describes your Haskell bindings. And this single data type is used for 2 purposes, one of which is this guiding generation. So we call prescriptive binding specifications. They provide a way to provide fine-grained customization of how bindings are generated. So for example, you could use these to customize which Haskell names are used, which instances are derived, which are generated, as well as what the representation of different types is. So for example, sometimes you want to have a type that's opaque. So these binding specifications are exposed to users as either JSON or YAML files. And this is an example of customizing a name using a YAML file. So here we specify that some type named linked list that's exposed by header example H needs to be given the Haskell name linked list in Pascal case instead of with the underscore. So these binding specifications can be generated, and then so you can generate your binding specifications and then customize them. Or if you want, you can write them by hand. So for example, if you have a library that has types that you want to use in your bindings, you can write binding specifications to make sure that those bindings are used. The second purpose of binding specifications is compositionality. This is the same file format, but the use is different. So we call these external binding specifications. So they allow existing Haskell types to be used instead of generating new ones. So a simple example is a library that has a network, HTTP, and TLS components. if you were to generate bindings for HTTP and TLS separately and include the network types, then each module for HTTP and TLS would have separate and distinct definitions of the types. So those aren't composable. You can't use them together. So instead, first, you would generate bindings for a network module. And while doing that, that generates the binding specification. And then when you generate bindings for the HTTP and TLS modules, you use that generated specification file as an external binding specification. And that ensures that the types are imported from the generated module. Since the generated modules have the same types, they can be composed together very easily. And again, you can write them from scratch. One other complication in generating binding specifications, or in generating bindings, is to determine which parts of a library you want to generate bindings for. And to solve that, we have selection predicates. This allows users to select which declarations to include or exclude from generated bindings. So we have you can select and exclude based on the header path or the declaration name. In addition, we implemented program slicing, which allows users to select transitive dependencies. So for example, I have two very common examples here. One of them is that you have some kind of library that you want to create bindings for, but you don't want to select all of it. You just want some subset of the library. This is a very complicated library. You can use the selection predicates to choose which part of the library you want to select, but you also need the dependencies of that part of the library. And if you had to create selection predicates for every single dependency, that would be very hard to first determine and then maintain. So you enable program slicing, and then all of those are included by default. And second, it's very useful for also including bindings of, including the dependency types. So if you want to create bindings for one whole library, but it also has dependencies, and you don't want to have separate libraries for all those dependencies, you can use program slicing to pull the needed types of all the dependencies into your library. Before I mentioned that types can be made opaque, and program slicing also takes that into account. So if you create a prescriptive binding specification to make a type opaque, then program slicing will not pull all the dependencies of that type. Macros are a very complex case because macros are handled by the C preprocessor. And so LLVM can tell us where macros happened, but it only tells us the result of the macros. So in HSBindGen, we have to reparse the underlying tokens and create our own implementations. So there's three cases of macros that I'd like to cover today. The first is constants. This one's very trivial. If you have a hash define, on the left we have an example with an integer, on the right is a double. We just create a direct binding for that type. You'll note that these names are not very pretty. In C, it's common to have constants as all uppercase, but in Haskell, we have to have our first character lowercase. But this is all done on purpose because it's better for us to understand where the names are coming from than to have to memorize the complex translation rules. Another case is for types. So a hash define can also be used sort of like a type def. In this example, there's a pointer int, which is a type for a pointer to an integer. And we translate this to a new type wrapper around the underlying type. This is done to support the preservation of semantics. And then expressions are much more complicated. In this example, we have a C macro that defines a function reg pointer that takes some argument that's named pointer and then adds 12, some constant 12 to that pointer. And the name of the argument indicates that this is probably a pointer, but it's not typed. So in Haskell, we need to generate an appropriate polymorphic function that's a translation of this C function. And to do that, we use type families to model the C semantics. So here, this specific function uses the add type class that has two type parameters that indicate the type, the first of which is polymorphic, and then the associated type add result is the result for your specific platform, because all of this is platform independent. So per platform, we have different C semantics, and the type classes are generated accordingly for your platform. So if you pass a pointer, reg pointer will return a pointer. If you pass up an int, reg pointer will return an int. And finally, I'd like to talk about a quick case study. This is the PCAP packet capture C library. It's a really old but well-tested library. And this is an actual command used to generate it, so it exposes some of the details. We have to have GNU extensions supported. We want to select all of the library, but PCAP library has some deprecated functions inside of it. And if we select those, then you might get linker errors. So we have a select except deprecated predicate as well that can use the C annotations to automatically remove those deprecated functions and avoid those errors. And we're outputting to the source directory into a module named generated.pcap. And this library takes about, so all of the type module as well as the function modules together take about 156,000 bytes, covering more than 4,000 lines of code. A lot of it's very straightforward, but I wouldn't want to write it myself. HSBindGen is a nice way to create these, or at least bootstrap, for if you want to be able to maintain them yourself. Here's an example usage, which you don't need to read through. This is just the most interesting usage that I could make that would fit on the screen. This finds all device names using the PCAP find all devs API. And this illustrates that it's still C. You have lots of memory allocation. We're traversing a C linked list. And this is an example of our low-level API that we're currently working on. And in the future, we're going to work on more higher-level APIs to make this a little bit more palatable. We also generate Haddock documentation. So here are the excerpts from the find all devs and free all devs functions. The PCAP library does not include any documentation in the headers, but we generate documentation that tells you the C declaration, where it's defined, and which headers it might be exported from. If there is deoxidation documentation, we translate that to Haddock as well, and then also attach these additional information. So I hope that some of you are wondering how soon can I use HSBindGen. I know personally I'm very excited to start using it in projects. We're currently working on the low-level API, and we have a release coming soon, so please check it out and try it. And we have a plan to create a high-level API as well to make it more easy to use for Haskell. Thank you.
Okay, we have about 8 minutes for questions, plenty of time.
When you bind a function, the function can be pure or impure.
Yes.
And if I have a sine or cosine mathematical function, yes, and can I control it's not IO double is the result of the function? Can I get some control of that?
Yes, yes, we support having pure functions as well.
This is great stuff, and I would like to use it, but then I noticed that this is not really Haskell, it's GHC Haskell.
That's correct.
And now I'm sad.
I have two questions. One is about the user live clan. You mentioned that you use for the HSBindGen.
Yes.
So do you actually somehow bootstrap the usage for live clan so that it generates the HS binding for live clan?
We've considered that, but we're bootstrapping it manually. So we have a separate function, separate smaller core that uses, it will go through the C header file and generate our libclang bindings. But it's not HSBindGen itself.
And the second question is that how do you deal with the C name length limit, like as you mentioned?
Right.
I mean, if there is a length limit for say some specific number, but if there is a nested struct, then it will easily go over the length limit.
So those nested C names are all internal. They're on the Haskell side, the HS Engine side. And we only have to worry about the C name length when we're generating functions, because we have to generate those wrapper functions that are in C. And so for those, we use hashing to ensure that there's a constant fixed length of the functions.
I have an actual question. Can you go back to the thing that had the regputter macro?
Which macro?
That one, yes. Now, if that was actually the macro, then that is not the right thing there, because if I use that macro, regputter with some p, and then it says ×3. When you expand that macro, that ×3 will be applied to 12 and not the whole thing.
So you would like to have, for instance...
So I'm just wondering, do you recognize that if macros are sort of used in a weird way, where it's you're actually using the token pasting rather than used it as a function?
That's a good question, and I'll look into that further. First, we implemented our own ad hoc macro parser, because we have to look at the underlying tokens given by libclang, and we have since been re-implementing it to use an existing Haskell library for parsing these things, and I will check.
I mean, I don't see what you could do if that was the actual macro.
Right.
But I would like to be told that.
That would be very
I
nice.
couldn't deal with it.
Very nice feedback. Thank you.
Thank you very much for the talk. I've actually used the tool a little bit. Edsco got me onto it when I was complaining about C things in the past. In my previous job, I committed some horrible sins in the C preprocessor using X macros, but functional X macros, which pass macros to macros. And I was wondering if this had any chance of being able to make any sense of much more complicated uses of the C preprocessor than it's a relatively simple function, but if it took in other macros, is there any chance that that could be type checked? I'm not even sure that there is a type that could make sense for those usages I have.
For macros, we're covering like the simpler cases first, and I think we can handle pretty complex functions, but if there's something that we don't know how to do, we just fall back to the expanded version. And if you have any test cases for us, we can try.
I can give you some horrific ones if you'd like.
Yeah.
Hi, Travis. Great talk, great tool. You mentioned that it's target specific. So you either have implicit or explicit in the generated code. I was just wondering, do you record the target, the implicit or explicit target you're generating the code for in the target specific files?
We do not currently, but that might be a very good idea. Thank you.
So we have two more questions, one to the left, one to the right. Richard, I think we're going to have to pass you.
Why not use duplicate field records for the structures and overloaded dot extension?
We are looking into doing exactly that. Duplicate field and overloaded dot. We're looking into it.
Yeah, that would be great. Thank you.
Thank you. So at Cubic, we built a tool with a similar purpose that generated outlang stubs. And one problems we ran into was C pragmas, underscore, underscore, something, underscore, underscore. Right. There seemed to be any number of those, and every time we upgraded the operating system, the header files would get new ones that our parser didn't yet cope with. You haven't mentioned those. I just wonder whether maybe you don't suffer them in the same way that we did, or
there's a lot of pragmas, and so currently we're supporting muscle, there's a libc and muscle, and we're trying to test on Linux, Windows, and Mac OS, and we have a fixed set of architectures that we're currently testing, and we're just testing extensively and trying to cover those cases because there's always things that pop up, and Yeah. Yeah, yeah. And in addition, like LLVM gives you a whole list of built-in macros at the very beginning. So every single file even if you're not importing from some standard library, you get this huge set of macros that you have to support. So it's a challenging problem. Thank you.
Yeah, one last question over there.
Yeah, I think twice during this presentation you talked about predictability of names, and I'm wondering, I don't really get who or what that predictability is for, because you know, it seems like you already generate this documentation which maps the names to their Haskell version.
Yes.
And people who are unhappy with the names are probably going to change the underlying C source or do some hack anyways. So I'm just wondering if you could comment on what the predictability you're talking about is.
Yes. So the names are also used in the predicates. So if you want to select, you need to specify a name that's our name after we name anonymous declarations. And in addition, in the binding specifications, which you use to specify to describe the bindings you want to generate, or for external bindings, these also have the C names in there. And we did experiment quite a bit. In the early stages of the project, we had ways to say, please generate more Haskell-like names. And in the end, we determined that it's not worth it. And it's better to have a very, very predictable, simple version, and then allow you to customize when needed. But thank you.
Excellent. That's all we have time for. I see there's a lot of raised hands still. So meet Travis at coffee, and yeah, please thank him again.
session. And the first speaker is going to be Gergo, and he's going to be telling us how to use Clash to implement a FPGA for solving Sudoku puzzles. Gergo, please.
Yeah, thanks. So yeah, so this is a function of Perl, which I'd like to point out because there's not necessarily that much science in this. There's a big part of it is just neat, but I think it is neat, so I think it's worth sharing. So okay, so what is it? What are the various pieces of things that we're going to be talking about? So I'm going to very briefly introduce Sudoku, which is a combinatorial puzzle. And then there's a 2006 function of Perl by Richard Bird, where he derives a Sudoku solver written in Haskell, like a normal software Sudoku solver. And yeah, he derives it in his usual way of starting from a specification and applying and writing a really naive and horribly performing version, and then applying a succession of program transformations to it to get something that performs well. Is very nice, like reading it is nice, and the way you get there is also very understandable via these steps. And then what I'm going to do is I'm going to translate that onto something that runs on an FPGA. And the tool I'm going to use for this is Clash, which is a Haskell to FPGA a compiler that takes Haskell programs and compiles it to FPGA configuration. So it's going to be, yeah, like a putting together all these things. And if that sounds familiar, that's probably because you were here on Monday and you heard Satnam's keynote, because I think this matches very closely the aesthetics of the approach that he was advocating for hardware design. And I also hope that you went to that meetup, because I think I can use that to skip over maybe some of the introductory stuff. Okay, so Sudoku is a combinatorial puzzle game where you're given a grid like the one on the left-hand side. In this case, it's a 3-3 Sudoku. So you have a 9x9 grid, and you see that it's divided into rows, columns, and 3x3 boxes. And you want to fill in the missing, like the empty squares, such that the digits 1 to 9 appear exactly once in every row, column, and box. And so on the right-hand side, you have a solution for this. So it's like your goal is to go from that to that. And like there is not necessarily a unique solution, blah, blah. But let's see if we can solve one. And just a small thing. So we can generalize this. You can generalize the Sudoku by its size. But note, and people normally think that the standard Sudoku is like the 9x9 Sudoku. But that's actually not a very precise definition, because these two are both 12x12 Sudokus, but they have very different constraint structure. So it's a 3-4 Sudoku, because you can see that you have 3x4, you have a 4x3 matrix of 3x4 boxes. And here we have a 2x6 matrix of 6x2 boxes. So even though the sizes are the same, they have different constraint structure, because this guy is a neighbor of this guy, whereas this guy is not a neighbor of this guy. They're not in conflict with each other. Okay, so we want to solve this problem, and we're going to solve it using Clash. So what is Clash in its essence? So the usual way of describing synchronous digital circuits is this so-called register transfer level abstraction. So you have a bunch of these registers, and they are clogged, hence the synchronous part. And you have feedback loops via these registers. So they are connected to each other and connected to themselves. Like you can see that the value of the register that comes out, the Y, feeds back into some combination of circuits. So this fun, imagine that it's just like a network of stateless circuits. And then it also has inputs from other registers like the X, or maybe it's an input from the outside world, and then Y might feed into an output from the outside world. So you have a network of these, and that's basically what you want to describe when you're working at the RTL abstraction. And so what Clash gives you is it is this. Like anything else just follows from the fact that there is a type constructor called signal. It is indexed by the clock domain so that you can't accidentally connect two registers that run at different clocks, because you really don't want to do that without making sure that there's some meaningful synchronization happening there. And then you have register, which is a primitive that takes an initial value for every register, and then implements like this box, right? So it takes a signal of type A, and then whatever comes out of it will be at the next cycle is what you get as the output. And to be able to connect these registers, it's an applicative functor. So that means that the pure parts of the combinational parts of your circuit can be described as pure, and the connections themselves become applications. So as an example, like this network we see here, we can describe it saying that, okay, y is equal to a register that starts at some value, let's say 19, and then it's updated in every cycle to the result of applying fun, which would be some pure function, applied on x, which is like some input from the rest of the circuit, and y is the thing we're defining. So this is recursive, right, in y, but note that the recursion is guarded by the register call, and that's the important part, because that's why it describes this circuit instead of describing some not really meaningful circuit where you have a direct feedback line. And also, yes, you can see, sorry, just one more thing. So you can see that its type is unsigned 5, which means it's a 5-bit wide unsigned number. And this might sound exotic if you're used to software, like a 5-bit, we don't have 5-bit values. But of course, if you're working with hardware, you have much more freedom on like the width of things, because at the end of the day, it really is just 5 parallel wires that you're gonna manipulate somewhat consistently, but it's still 5 signal lines. So why not have 5, just as easily as you can have 8 or 64? Okay, so that takes care of the clash part. And as for our approach to solving Sudoku, so there's this function of Perl, and we're going to use a specific, so like it's a step of refinement. And we're going to use a specific step in that process from that paper, which is a classic backtracking algorithm. So, you have an internal representation of the solver state, which consists of the candidate values for every cell. So you have your 9x9 grid, and then you know what are the values that are still possible for each of those cells. And then you do pruning, because if you know that a given cell can only be a given value, then you also know that all its neighbors can't possibly be that value. And you just keep doing this. Like you keep turning the crank, because when the result of pruning might be that a cell becomes a singleton, like a value that only has one possibility. So now that itself can help in pruning other neighbors. But at some point, you might run out of things to do. Like you get into a situation where there's no more pruning to do. And that's when the backtracking comes into play. So basically, you make a guess. And you just try solving the guess. And if that doesn't work, then you backtrack. So this is a slightly rewritten, reformulated version from the paper. But the details don't matter that much. The basic point is that given some Sudoku grid, we have a bunch of branches. We detect if we need to backtrack. We detect it. Well, actually, so the backtracking is kind of implicit here, right? Because what we do is that when we are blocked, when we know that there's a conflict, we just return empty, like this runs in any alternative functor. And then when we need to guess, there's this expand function that gives us all possible guesses that are still consistent with what we know so far. And then we just take the alternative sum over trying all those directions. So this is software, right? This is not Clash code yet. And okay, so then we want to turn this into hardware. So the very first thing is that the circuit is going to be like a real circuit. It's going to have a fixed structure. So of course, it's not going to be polymorphic over all alternative functors. So we're just going to stick to maybe, which means that we're going to get the first, or like we're going to get one solution if there is a solution, and we're going to detect if there is no solution to the given Sudoku problem. By not having a solution, I just mean that the initial constraints were inconsistent. So the next step we need to do is to make sure that everything is using fixed size representations. So, no lists. So the Clash standard library gives us length indexed vectors. And then we can, of course, use 2 levels of that. Like a vector of vectors is a matrix, it's a 2D structure. And then to make it easy to track this structure, you know, the 3-4 Sudoku versus 2-6 Sudoku, we're going to represent the grid as a matrix of matrices. So it really is a 3x4 matrix of 4x3 matrices of cells. And what is a cell? Well, I said that the internal state of the solver is all the possible values that are still valid for a given cell. So we're just going to use a bit vector of the right width to represent cells. And so now we can say that an NM Sudoku board is just an NM grid of n times m long bit vectors. So the main operation that we need to be able to do efficiently is pruning. Because like other than pruning, we're doing like guessing. And of course, the whole point of doing the pruning is so that we don't have to guess that much. Because, you know, like the stupidest possible solver you could imagine would be one that just tries guessing everything and hopes to eventually get. But that doesn't work for Sudoku. I mean, it's an exponential block, right? So you want to improve that by pruning. So we can implement pruning by representing masks separate from cells, for the very simple reason that we only want to include cells that have only a single possible value in masking. So we can turn a cell into a mask by saying, okay, is this a single value? If so, then the mask becomes the same bit string or bit vector as the cell itself. Otherwise, we want it to be neutral in some sense. We will get back, like you might say, okay, I'm using M empty here, but I haven't given a monoid instance to mask yet. So what's going on there? I will get to that in a minute. But just one thing I want to point out before that is, of course, we could compute the singleness of a cell from itself. Like there's no point in passing a Boolean telling us if the cell is a single bit or not. We could just check it. The reason we don't do this is because, as we will see, we're going to do it in many different contexts where we need this property. And we want to share that. We want to have a single piece of circuitry for every cell that, like, I don't want to say caches it, but you know, like you want to share the circuit that computes whether a bit vector is just one, as just one bit. So how is bit mask? How is mask a monoid? Sorry, this should be mask, not bit mask. Sorry. So the basic idea is that pruning itself is a monoidal action, because if you have the mask, if you have 2 masks, which are just bits, right? Just bit strings. So if you combine them using bitwise OR, that corresponds exactly to saying, okay, so this can't be, this bit is not valid, this bit is not valid. So if I combine them, both of these bits are not valid. These are not possible values anymore. And that, of course, also means that the empty case is one where you have no bit set, because that means there are no position or no bits where I know they can't be valid, because I don't know anything yet. And then the action itself is just removing the bits from the set of candidates that we already know can't possibly be values of that given cell. And so if you, like, okay, you might say, okay, this is formally not a monoidal action, because like, what even is this bool? How does the bool come into play? But if you think of this morally, if you think of the bool as something that you could, in principle, compute here from the cell, then this would formally even be a monoidal action. But for us, really, all that matters here is that if you take the mconcat of masks and then you apply that on a cell, it really is the same as if you kept applying different masks. So the next thing we need is the constraint structure of Sudoku, right? Because so far everything has been on the cell level, but what we really want is for cells to communicate with each other via rows, columns, and boxes. And so what we can do for that is to say that, okay, any group consists of n times m cells, and then a full grouping is n times m groups. And if we do it as bidirectional functions, so like here you see that this A, B, both ways arrows just means you have a way of going from A to B and B to A. So if you use these 2-way mappings, then what that gives you is that we can fold over groups by basically going into the grouping, so reshaping our grid into a vector of rows or a vector of columns or a vector of boxes, and then folding each individual such group, but then we can smear that back into the original structure. So I have a picture coming up just a second that should show this, but let me just quickly show what the code looks like. So basically, we can say that if we have a grid of monoidal values, we can fold that via its 3 groups by folding it row-wise, group-wise, and box-wise, and then putting those 3 cell by cell, combining them using mconcat or mappend. So this is what is happening. So in this example, this is a 2-3 Sudoku, just so that it's small. So when we fold by rows, what that corresponds to is for every row, we take the monoidal combination of the masks, right? Like, so if I know that something has to be, like like this cell, right? It has to be 1. Like this is something that, for example, part of the original problem. Then in the first row, I know that nothing can be 1. So all of these cells, when you fold by rows, the mask that we compute from this, which is the one where the 1 bit is set, is going to be set everywhere. Because we first, and of course the 2, the 3, and the 4 as well. So when we combine these, we get 1, 2, 3, and 4. And then we smear it into the whole row. So now every cell in the row has the mask 1, 2, 3, 4. And the same happens for the columns, and the same happens for the boxes. And the reason we do it is because if you then look at this middle column, then if you put them together, so if you then like zip them basically, then for each cell, you're going to have both the cell that comes from all its horizontal neighbors and all the vertical neighbors and all the box neighbors, which is what you will get here. There's a slightly zoomed in version here. So we first fold by columns. Yes, we get the, so you see that every column now gets the same value, which is the combination of everything in that column. And then when we put it all back together, these 3 neighborhoods of every given cell combine to give us the mask of everything that can see that one cell. So yeah, and that is basically what pruning is, because then you just apply the monoidal action of these masks on the values that are there. And of course, remember that for values where we have only one candidate, masking or pruning doesn't do anything. That's the whole point, that we already know what those values are. Okay, so then the next thing we need to do is branching. So original software version returned a list of guesses. That is problematic because like a list is not good for us if you want hardware that actually manifests this structure. But you don't need to guess n way. It's enough to guess 2 ways if your second guess is something from which you can continue guessing further and further if you need to. So the way we do that is we can split every cell that is not a singleton. We can split it into its least bit, and that is set, and all the other bits. And why the least bit? Well, I can refer you back to an ICFP talk from Tuesday, I think, where Brent Jorge's Fenwick tree Perl showed in great detail why you can compute the least set bit of an n-length bit vector as just a negation and a bitwise AND. So this is like super, super efficient to implement in hardware. And also note that once you remove the 1 bit, like the least bit, if what the rest is all 0, that exactly must mean that you only had 1 bit. So the reason that we were passing this is single as a parameter everywhere is because we can actually get that for free from here as well. Okay, so the next thing we need to look at is the fact that this is still recursive. And recursive, if you think of this as just really just putting it into hardware, that would mean you have like this infinitely big circuit, because every time it recurses, it will need a copy of itself. Of course, that's not what we want. What we really want is to have something that over time uses the same 1 copy of the circuit to make progress. Like in every cycle, you would do something by pushing things through the same circuit. So okay, so how is this recursive? Well, it's recursive two ways. It's both tail recursive and also non-tail recursive. So the tail recursive thing is very easy to imagine how to solve that. You really just need a register and then the current state comes out of it, and you feed it back in by pushing it through the same circle. And for the non-tail recursive thing, what you really want is, so first of all, we make a pure function. This is still in the world of pure functions that does one step of this recursion. And then this is what we were going to do in a single cycle. And then we write some stuff around it that implements a stack of these. The second, like basically, you know, when you guess and you branch two ways, the second one is the one you will push on the stack so that you can get back to it when you discover that you're blocked from further solving, because there's a conflict. And so here you can see a model of this using a Haskell list as the stack. But of course, this is not what you can do on hardware. So what you can do on hardware is you can use a piece of RAM to implement this stack. So we basically use a primitive from Clash where, given a memory command of n cells and data of type D, it will give us in the next cycle the read result of the previous cycle. And the stack frame itself is just a Sudoku board, right? Because the continuation is just something where the guess that I have already made is no longer valid because I came back here, I arrived back here because I realized that that guess is not going to work. And this also means that we know the stack size, I mean the limit on the stack size, because it can never be more than the size of the Sudoku board, because every time you guess, you make one of the cells into a singleton value, and we never touch those other than backtracking. So everything is nicely finite and fixed size. And that's basically it. And then there's the rest of it, which is like, you know, the difference between, like in the software world, right, you write a function, but you also have to write main to make it into a program. So the rest of it is I/O. So this is a standalone device. So you load it onto your FPGA, and then you can communicate with it via serial link. And then you just basically connect either like your computer, or you take your 1970s terminal and plug it in. And then you just type in your Sudoku board, like you see here in the left-hand side. And there's some very fancy parsing going on, because basically we ignore everything that is not a digit or a dot. So this allows you to have this nice ASCII art. It's completely ignored. You don't need this. You could just type in the numbers after each other. But this is very nice because it allows you to copy-paste human-readable problems. And then what comes out of it is this thing that you can see that is nicely formatted. So this really is the output format with the extra spaces to emphasize the n times m times m times n structure of the board. So the whole thing hangs together by basically, we can do the same thing as software Haskell's interact function, which is like, so interact takes a string-to-string function and gives you an I/O unit, right, where every line is pushed through that function and what comes out of it is printed. So using this library called Clash protocols, we can then compose our Sudoku solver plus the controller of it. So the controller here is the thing that handles the stack, basically. So this we can compose with the parser and the formatter. So the formatter includes also injecting these white spaces. So we can compose that, which you see here. And then we can use we can actually write a general serialized combinator, which, just like interact, takes a circuit that produces and consumes bytes into something that produces and consumes a serial transmission line. And you can see, of course, that I'm using type application syntax here and here and here, just to emphasize that, first of all, this is the code itself is fully generic over the size of the board. But of course, we need to instantiate it to a given board size to produce a concrete hardware. So these two threes are just the fact that it's a 3-3 Sudoku. And then the speed of the serial link is 9,600 BPS. And that also has to be on the type level, because we do some type level computation to compute the clock divider for your FPGA to implement that specific speed. And of course, now with the recent enough GHCs, you can use the require type arguments extension so that this, you don't need the ats then, and it really just looks like a function application, even though that 9600 is a type level argument. And so that's basically it. So what is it that we achieved? So first of all, it turns out that it's super nice to use Clash for anything because the testing on the software side is really easy. Most of this stuff, like all this monoid stuff, that's on the pure side, right? So you can just test that as normal, pure Haskell functions using whatever Haskell testing methodology you want. And Clash has a simulator which you can use to do the integration testing. So if you want to include all these other parts in your testing, you can do that because Clash basically gives you a way of running or simulating a signal cycle by cycle, and you can even interactively, like you can do it in I/O and then feed in the inputs and so on and so forth. As for performance, so in the simulator, we can very easily count cycles. It's cycle-accurate simulation. So we can see that most realistic 3-3 Sudoku boards are solved in less than 100 cycles. I don't know what your CPU can do in 100 cycles, but I'm pretty sure it can't solve a Sudoku problem. But there are some hard problems where it could take as many as thousands of cycles. So like that could, yeah. And then on a real hardware testing, so I took a Xilinx Atrix 7, which just by accident happens to be very similar to the one that Satnam was showing at his keynote. This is like a slightly smaller version of that. But with just the default settings, I didn't really try to find the fastest clock or anything. Just defaults to 100 megahertz, why not? It means that tens of microseconds is all it takes to solve a Sudoku problem. And as for the size of the circuit, so the proprietary Xilinx Vivado synthesis tool synthesizes it in about 10 minutes, which is not too bad actually. It's like these tools can sometimes run for a very long time, even on these small boards. And the resulting circuit is about 9,000 logic cells, so which is about a third of this particular FPGA model for the 3-3 solver. Now, of course, the scaling is, in terms of size, is not so good because the whole point of this exercise is to use all the FPGA we can. So, we do all this propagation. Every single cycle, we propagate all immediate constraints because we have the structure that connects everything to everything. So for the 3-4 Sudoku problem, the logic cell usage shoots up to 25,000. So it kind of barely fits into the same FPGA. But for the, do you have time for just one more small tangent? Okay, so if you think about this stuff, right? Like if it fits in if it uses less than a third, that means you could fit 3 of this. And so when we pick a cell that we want to split on, there's absolutely no heuristic, when we are guessing, right? There's no heuristic on it. So what we could do is we could have 3 different ways, like maybe pick the first one, pick the second one, and pick the most middle, like the one that's just halfway between them. And we could race 3 solvers and then see which of them finds the solution first. So there is, like the future work to explore this, that given that it fits multiple times, how can we very nicely in the Haskell or in the Clash code express this idea of basically the hardware version of AMB? And yeah, that's basically it. So the takeaway message here is to check out Clash and use Clash because it allows you to write interesting hardware in a, I think, very nice way. Because note that all that stuff about monoids and monoidal actions and whatever, all this is really in the Clash code. We never had to that was not just to explore the solution space, right? This is what the final Clash code looks like, which is, I think, a real benefit to this approach. And yeah, and that's it. So yeah, thanks for.
Thank you for the talk. We have some time for questions now. There.
Yeah, so I have a general question about Clash. So So Clash on the surface is very similar to Haskell, right? You can say it's a subset of Haskell. So I wonder if you find it to be the case, because the target runtime is very different than the regular Haskell runtime. There's probably like no lazy evaluation in FPGA or whatever hardware it targets. So do you find it to be the case that a lot of the the idiomatic ways or good practice of writing Haskell are actually bad practices of writing Clash? It could lead to like very inefficient code, or if not incorrect code. Do you find that to be a problem?
Okay, so there are two parts to that. One is that situations like this one, like with recursion, where this is not valid Clash. Like this can't be synthesized into hardware because it's recursive and there's no finite circuit that corresponds to it, and then you have to solve that. The other situation is where, so this is single thing, right? So I said that, we can just get it for almost free by comparing with 0. But if you think about what exactly is going on here, it means that for every cell, we're going to compute this split into 2 cells, right? But in a software version, you might think that, this is very expensive, like this is needlessly expensive, because if I want to split my whole board, I can stop at the first cell that can be split, because because the whole point is that we want to find a guess, so just pick the first one, and then I don't need to look at the other cells. And if you look at it like that, you might say, but then it's not really free. Actually, it's a very roundabout way of computing is single, because now I need to compute all this just to finally find that the bit count is 1. But in hardware, the cost model is different in that sense, because you have, like, if you have a branch, right? Like if you have a branch on, is this the first cell that can be split? That branch just corresponds to a multiplexer, but the parts are already going to be used for both branches. So if you have 81 such small circuits, and then you need to pick the first one, then it's for anything else that comes out of the 81 small circuits is for free, because you have to have those parts anyway. So in that sense, the cost model can be different.
Okay, so it does require you to think somewhat differently when you write Clash compared to.
Well, yes.
I wanted to expand on that a little bit, because I've spent quite a bit of time working in Clash, trying to convince a previous employer that we should use it for things. And the programming style that you use is very much not idiomatic everyday Haskell, but it's very idiomatic stream processing Haskell of applying pure functions to applicative streams that are potentially recursive. And once you start to internalize that and the mapping of that to hardware, it's so much nicer than any of the other languages that exist. Clash is decades ahead of using VHDL. There are notions that you can express in Clash that there is just no idea of in these other languages. Adam sort of touched on this the other day, that the languages that are used for designing these circuits are so backwards for the job that they are used for universally, and then you start working in Clash. It's night and day, just how expressive you can start to be and how you can build these reusable components and have a type system that's not completely bonkers. So yeah, you aren't writing idiomatic everyday Haskell, but the code that you do write is just so much better than the alternatives. All of the Haskell extensions all get used in Clash for the things that they should be used for, expressing things in the type system about the invariance of your system that you can't easily do in other languages. I feel like you can turn on.
I think that this kind of abstraction you can't really describe in Verilog or VHDL. When I think, for any monoid, I know how to fold over my constraint structure. That's really, that's just not how you think. You can think about things.
You may have mentioned it earlier, but to get started in Clash, one needs an FPGA development kit. They're not typically sold in the usual to retail. So do you know how much it costs and how difficult it is to obtain one?
To get started on this stuff, $100 will get you everything you need. So I have a Flappy Bird circuit that you can find on my So on my homepage, which is like, yeah, so if you go to Unsafe Perform IO and follow some links, you can find some simple examples like Flappy Bird that plugs into a VGA or HDMI screen, depending on the board you have. And yeah, that would be like not even $100.
Any other questions? So one at the back there.
Hi, Gary. So my question might be a bit different to the others. So you said you wanted to raise multiple circuits in parallel as an idea. Do you know what the power draw difference then is?
Ooh, I have absolutely no idea.
I was just wondering, like, if these FPGAs, well, the FPGAs might be constant power draw in that, or you would notice like, if you're just having like 3 times as much on there.
Use parts of it or don't use it, whether it makes a difference in power. I would think it does make a difference, because if you don't use parts of it, the clocks don't even get connected.
Okay.
So
All right, we're running a bit late, but since we have plenty of time in the 2-hour block, I want to ask one last question. It's not very specific to this work in particular, but more to the work using Clash in general. So you've been doing this for quite some time, and as we've heard here, we believe this is a great approach, and I think this is also a great way to describe something that's very low level, in my opinion, at a very nice level of abstraction. But I don't think it's really used a lot in practice. Why do you think that is? What are the barriers to adoption so that more people are using this in practice?
So I think a part of it is that the people who are doing this like professionally, the people who are actual chip designers, etc., like they don't necessarily come from a culture where the axes in which Clash shines are really acknowledged. So I think there's a big part of like there are cultures where if if you get the right output for the right input, the job is done. And I think it's very hard to sell on abstraction or on levels of abstraction, or sell on tooling in those cultures. I think that's a big part of it.
Okay, let's thank the speaker again. Our second and last speaker for the day, because the third session that was earlier scheduled was moved to tomorrow. Samuel is going to talk to us about improving an earlier implementation of automatic differentiation using staging and fusion. Whenever you're ready, please go ahead.
Yes. Hello. Today I will be talking about staging automatic differentiation with fusion. And what I mean by that is that I'll be telling you how to write a fast but also correct compiler for automatic differentiation. Automatic differentiation, of course, being that set of techniques with which you can compute derivatives efficiently, avoiding the pitfalls of symbolic differentiation and numerical differentiation, and have this be both fast and as accurate as we want it to be. But first, I'd like to say something completely obvious, which is that a good algorithm is an algorithm that is fast and hopefully also correct. This is no less true for AD, but unfortunately, often faster and more sophisticated algorithms are also more difficult to prove about. And of course, for AD, we have a rich literature and a lot of work on how to write fast and efficient implementations, which sometimes come with impressive and complex proofs of correctness. But we also have some literature on how to write algorithms with simple proofs. But these tend to be a bit disjoint. Now, obviously, that means that for today, our goal is to write a fast algorithm with a simple correctness proof. On the topic of algorithms with simple correctness proofs, we already know how to make those. And in particular, we know how to make this one, reverse AD, which, like all AD variants, computes the value of an expression or the primal and the derivative of the expression or the tangent simultaneously. But if we use this to take the derivative of xyz at 1, 2, 3, it actually gives us back the derivative in a sort of backpropagator form. And to get the actual derivative out, I have to give it the 1 and 0 vector. But this gives me, obviously, the correct derivative. And because this algorithm is calculated, it becomes correct by construction. And by using this backpropagator form of the tangent, it's also asymptotically fast. However, the derivative is computed by recursively combining these backpropagators. And it turns out that combining these backpropagators in this form is actually a bit expensive, and this makes the algorithm relatively slow or have a large constant term. So the situation we're in is that we know how to make a fast and easy to prove correct algorithm, asymptotically fast, I should say, but it is relatively slow compared to other implementations. In contrast, I could have just given you this not very self-explanatory piece of code, which also computes the derivative of xyz. But here you'll just kind of have to take my word for it that it does. However, the good news is that this is exactly the content of our paper. And in fact, I won't give you this piece of code. I'll tell you how to compute or calculate, derive a compiler from reverse AD. And to do this, we'll first prove quote fusion. And this will give me from reverse AD a simple but not very good compiler. And then I'll demonstrate how we can apply the principle of fault fusion to gradually turn this compiler into a slightly better compiler. And along the way here we'll discover how to integrate monetic sharing into this approach. And to finish this off, I'll demonstrate how you can actually very easily extend this calculation with even further optimizations. Now, before I can start calculating, I'll actually have to tell you what this mythical reverse AD algorithm is. And this algorithm, actually, before we can even start taking derivatives, we need expressions to take derivatives from. And in this case, I'll use the polynomials. Expressions, of course, exist to take derivatives of, or, well, to be evaluated, I should say. And in particular, we'll evaluate them into numbers. And in our case, these are just things with ones, zeros, addition, and multiplication. Okay. When I use this evaluation to evaluate an expression, xyz at 1, 2, 3, it again goes on and recursively combines the results of x, y, and z to give us the final result 6. But if I wanted to take derivatives, I could also use eval. But this time I'll use eval on dual numbers, which are just fancy pairs of numbers and their derivatives. And we can give these dual numbers or we can treat them as numbers by reading the rules of differentiation as their operations. And because now dual numbers are numbers, I can also evaluate into dual numbers. And if we do this, you'll see that we recursively combine the derivatives of the sub-expressions to get the derivative. And actually, you might note that this algorithm corresponds essentially directly to forward mode automatic differentiation. But we wanted reverse mode automatic differentiation, and the way we'll get there is by using fault fusion. And fault fusion says that if I have a homomorphism H, and being a homomorphism just means that it preserves some sort of structure, which in our case is like zeros, ones, addition and multiplication. Then if I evaluate and then apply H, this is actually just the same as evaluating with H. And what this means for us is that if I hit forward mode automatic differentiation sufficiently often with fault fusion, I can get reverse mode automatic differentiation. And this, in effect, tells us that it is correct by construction. Great. We'll extend this calculation by taking reverse AD and turning it into a compiler and having it produce code somehow. And the somehow here is by using stage programming. To do stage programming, we'll use template Haskell. And in template Haskell, we don't have one, but we have two stages of execution. We can write code for compile time and for runtime. And template Haskell adds the syntax for quoting expressions, with which I can put quotes around an expression and get the code of that expression. And conversely, a splice operator with which I can turn code back into runtime code. And what this allows us is this, that we can write programs that run at a compile time and produce code, and we can splice them back to produce programs at runtime. For example, we could consider the power function, and rather than defining it recursively, I can now just generate its function body, and we do this by defining the following make power function. But essentially, this is just the power function itself, but with some quotes and splices inserted in tactical places. And if we use this, for example, let's say we use it to compute the power of 4, x to the power of 4, we get the code of x to the power of 4, essentially. Now, the idea is that we can actually do something very similar to reverse AD. And I'll reiterate the approach of our paper, which is that by doing this, we stage reverse AD, and then we can optimize it. So the first thing we'll do is we'll stage the evaluator, and this will give us a not very good compiler. But then we can apply fault fusion and gradually make a bad compiler slightly better. But if we take the straightforward way, we'll actually run into an issue known in the AD literature as expression swell. But we can now easily sidestep this by using monadic sharing. Oh, that's small, okay. So let's get started. To stage the evaluator, I'll first actually note that the operations on numbers actually quite directly induce operations on code. In particular, I can just write the 0 of code as the code of 0, and if I want to multiply two pieces of code, I can just put a multiplication sign between them. And in effect, this turns code into a number, and numbers are things I can evaluate into. Oh, Yeah, well, here's an example. For example, if I multiply 2 and 3, you get 2 and 3, okay. But now I can also evaluate into code. And for example, if I take the expression which essentially represents x times y, I also get back the code for x times y. And in other words, this actually means that eval has just become a compiler. Crucially, of course, it should be the case that compiling x times y actually gives the same result as interpreting x times y. And we proved this in our quote fusion theorem. We actually proved this in general for all kinds of folds, but I'll give the specialized form here. And essentially it says that quoting the evaluator is no different from evaluating into code. And this has two direct corollaries, which are that eval as a compiler is actually just the same as eval as the interpreter. And this directly applies to reverse AD, which is eval in disguise. And this will give us a compiler. Now this compiler is not very good because it quite literally dumps the input expression back into code. But we can improve on this by breaking up larger pieces of code into smaller, more manageable ones. And for that, we'll use the following homomorphism, which says that I can take a tuple, or the code of a tuple, and I can split it into a tuple of code. And by fusing this map into our compiler, I can now manipulate the primal and tangent separately again, and I can actually statically evaluate the multiplication here. If we do that, we get this. And this looks somewhat good, but it's actually not very good, because, as you can see, V1 and V0 actually appear in multiple places, which means that we're going to start computing the same thing many times over. So, well, we started from this multiplication and we ended up with something that looks like what should be the result. We would actually prefer if we could share these values between the primal and the tangent in a way something like this. Fortunately, this is something we can easily do by using a kind of continuation passing style code generation monad, in which we will be able to explicitly perform monadic sharing or let insertion. And the way we incorporate this into our calculation is, once again, by performing fold fusion. And this time we'll perform it with the return of the monad. Now, this gives us the next compiler, which does a little better, as you can see, and it has even simplified the multiplication without making a duplicative mess. But we actually can do better, because you can see that there's still these unreduced operations in the output of the compiler. However, I suppose that by now this approach is getting a bit boring, because we're going to actually repeat the same couple of steps very often now, which is simply that we'll note that the compiler produces some unreduced expressions in its output. Then we'll find the appropriate homomorphism to reduce these. When this seems to cause a mess, we'll apply monadic sharing once more. And then we can just fuse this homomorphism to get the next slightly better compiler. And I'll do this a couple of times over, but I'll spare you the details because the paper gives you those. but I'll summarize that we'll once take apart some functions, and this will simplify scalar vector multiplication. Then I'll take apart some other functions, which will simplify vector-vector addition. And then finally, we note that map is essentially traversable for code, which will simplify insertions. But I promised that this approach, extending this approach would be easy. So let me do that. And as an example, I use constant folding. So for example, if we have the code, or if we take the code of 2 and 3 and try to multiply it, how can we simplify the result? For this, I'll build a tiny language around code in which we can distinguish between dynamic and static values, and we also distinguish between static zeros, ones, and other constants. And for example, I can equip this with the operations, which just say that if I multiply two statically known numbers, this is just statically another constant. But if I multiply a number with something dynamic, I get back something dynamic. And we can show that this is correct, you might have guessed it, by using another homomorphism. So in the end, this finally gives me the promised compiler, and I'll very creatively name it comp.ad. And as you might have expected, applying it to the expression xyz gives us this code. And as you can see, it no longer mentions any operations on vectors, maps, and such. These have all been statically reduced. But this time around, you no longer need to take my word for it, that it computes the right thing. We actually know that it does, because we know that it comes from this compiler, which we've shown correct by construction. Now we actually went on and figured out how much faster this makes everything. And for that we wrote some benchmarks. And we compared our compiler against JAX, a Python library for AD, and AD, a Haskell package for AD. And I'll note that we'll use double precision. We do allow vectorization, but to level the playing field a bit, we run everything on a single core. And furthermore, I'll note that the omitted data points actually represent crashes, which usually are out-of-memory ones. So while this does make the benchmark a little bit less realistic per se, it does give a good indication of how much faster we've made our compiler. For the first benchmark, we tested a linear least squares problem, and as you can see, we have a good start and we perform quite similar to JAX. But JAX tends to still be a bit faster. I think the behavior on the right is actually a bug in JAX. I didn't look too deep into that, but unfortunately, before we get there, we also crash. We also benchmarked the logsum x function, and as you can see here, while we beat AD by a factor of over 50, we do get beaten by JAX quite significantly, and for a good reason, because as you can see, this problem is quite amenable to vectorization, and JAX can make use of this to get a decent speed boost, while we do not, obviously. Yes, and this will come back in the future work. And finally, we benchmarked the naive definition of matrix determinants. And as you can see here, we actually significantly beat JAX and AD. So to summarize, we once beat JAX, we once almost tie it, and once we get significantly beaten by JAX. But to conclude, I have shown you how we can calculate a compiler for AD, and this reduces the performance gap with more popular AD libraries. But by virtue of its construction, is automatically correct. And furthermore, it is also very easy to extend this approach with more features or with further optimizations. And before I wrap up, I'd like to mention some future work, which is, of course, that we could still improve the compile time behavior. And one way we could do this, for example, is rather than compiling Haskell code, we might consider compiling to different languages. And the other obvious one is, of course, is looking into how we could extend our calculation with factorization. And if we're lucky, then maybe we can get closer in performance to JAX. And finally, I'd like to summarize some of the details I glossed over in this talk, but are very present in the paper, which are all of the preservation maps, of course, the entire calculation. And in the artifact, you'll also find a mechanized proof of quote fusion, along with, of course, the implementation, which includes all of the calculation and the benchmarks. That's all. Thank you very much.
Thank you. We have time for questions now.
I found the commutative diagrams in your slides quite helpful to understand what is going on. And I'm saddened to find that they are not in the paper. Do you have a version of your paper with those commutative diagrams?
Not yet.
How do you handle recursion?
We don't. So actually we work on a very simple language of just these expressions.
Yeah, but you also said it was easy to extend your language.
Yes.
I mean, if you come from the financial world, you might run something that takes half an hour to run and it's full of loops. So
yes. So of course we could extend. So first of all, this language doesn't actually allow you to share values yet. It is just polynomials. So first, we'd have to extend this calculation with let binding in the source language, which is actually something that is discussed in this paper in the top right. So first of all, we'd have to extend our calculation with that. And from then on, I think it shouldn't be that challenging to implement like loops and other control flow.
how would you store all the intermediate values? I mean, you can't unroll the recursion because you don't even know how big it is. Well, we can talk.
We can talk about this.
Any other questions? Okay, I have a question. You said the missing data points were crashes, essentially, out of memory, likely.
Yes.
Can you say a bit more on that? Did you look at memory consumption, both in your
Yes.
as well as the JAX crashes?
So I believe in this one, we run out of memory during compilation. When we produce some template Haskell, and when we actually go and compile that produces something intermediate which is too big. Which is why I mentioned that translating this to a more primitive language might save us. Because hopefully, like a compiler for LLVM or maybe if we convert to assembly directly, would use a lot less memory. And for JAX, I'm not too well versed in JAX, but here very clearly in the just-in-time compiler for JAX, at least for a CPU, because in JAX you don't have very good support for recursion, so we define the determinant by writing this big loop over all permutations of the matrix elements, right? And this just somehow blows up before we do.
If no other questions, then I have another one. You take a sequence of steps in improving your compiler, and
Yes.
you argue, and I can kind of follow that there are improvements, but have you actually measured them midway through to check that each of them is an improvement?
Yes, this is in the paper, but I unfortunately didn't include that in the slides. We actually see that the very first step, in which we turn eval into a compiler, so we essentially dump the expression to code, this somehow produces something slower, but from there on, each of the steps improves everything by a small factor. And then at the end, of course, when we get rid of the insertions into maps, all of a sudden we go from logarithmic n log n time, we all of a sudden jump down to linear time.
All right, let's thank the speaker again. So this was the last session of the symposium for today. I believe there's the student research competition posters for SPLASH happening at 6 p.m. and also the reception. See you around.